equals to 4 means 4 by 20.
4 by 20.
Yeah. X follows uniform distribution 0 and to 20. So
0 to 20, yeah, 0 to 20.
So when so the range of y is between is 4 to 8.
4
So
to
if
8.
x, yeah, so if x is y is less than equals to 4.
4, y is less than or equals to 4 is 0.
Yeah.
So probability that okay, probability that y less than or equals to 4 is nothing but probability that y is equals to 4. So it cannot go
Yes.
below 4. So
Right.
as this is continuous, the probability at one point will be 0. Correct? So this
Yeah.
will be 0.
No, sir. Probability y is equals to 4 is when probability x is between 0 and 4. Then it is 4 by 20.
4 by 20.
Because y is dependent on x.
Correct. Yeah. So we get probability that y is taking 4 is nothing but probability that x is less than or equals to 4. So what is the probability that x is less than or equals to 4? It is interval 4, 0 to 4, 4 by total
20.
interval 20. This is 1 by 5. So
Yeah.
probability that y is equals to 4 is 1 by 5.
Yes. Now, if y lies between 4 and 8, and then it will be just
4 in integral 4 to 8 uniform, right? It will be just 4 by 20 again.
no y by 20, small y by 20, because 4 to small y.
Yeah, 4 to small. Correct. Okay. So we can do this like this. Correct. So y is less than 4 is one case, and y is in between 4 to 8, and y greater than or equals to 8. Okay.
Yes.
So y less than 4, y cannot take the range of y. First of all, range of y or support of y is 4 to 8. So y cannot be less than 4, so it will be 0. So 4 to 8. So y taking values between 4 to 8 is here also two cases will be there. Y is equals to 4 is one case, or we
Sir,
can directly
y
integrate,
small y
right?
takes values only from 4 to 8.
Yeah, only 4 to 8. So y taking values less than 4 is 0.
Yeah, like y greater than equals to 8 is also it's 0, because it is just from 4 to 8 y.
Okay, so we are including is equals to 8 here, right? Okay, we will come collectively write it. So y greater than 8 and here itself. So y taking values between 4 and 8 is simply 0 to 4, 4 dx plus 4 to 8 x dx. No. So equality we should take here on y greater than or equals to 8. Okay, this is what the inequality will. This is the value when y is in between 4 to 8. So when y is in between 4 to
Sir,
8,
you can
excluding,
yeah,
yeah,
you can do it uh, like for separately for 4 and for 8,
and
and
for
then
8.
you can take the 4 comma 8, that open interval. Because when y is equals to, when you are doing small y is equals to 4, then probability capital Y less than equals to 4 is probability x less than equals to 4, which is 4 by 20.
Hmm.
and probability when you take small y is equals to 8,
correct.
then also it is 12 by 20, and for the rest it will be y by 20.
Correct. So we can take it as a separate case. Okay, y less than 4, y taking value 4y to 8, y taking value 8, and y greater than 8. So this will be
4 by 20,
4 by 20, and this
and
will be 12
this
by
will
20,
be yes, this will be from
8 to
no
20.
it will be 12 by 20,
12 by 20, and this
and
will
that will
be
be 0 to y. uh,
4 to y. 4 to y x dx.
yeah yeah
Correct? So x square y2 y 4. Is this correct?
no, so can you just scroll up once? I'm like yes, okay, so
Okay, this question is week 5 tutorial 1 question number 6. So we are trying to find the CDF of y,
oh
where
sir,
y is
like
max of
when y is between 4 to 8,
hmm,
then it will be the CDF is probability capital Y less than equals to small y.
small y.
So it is, but capital Y is x. It equals x when it is between 4 and 8.
Yeah, less than y. So this will be probability that x is less than or equals to y. Okay.
Yes. So 0 to y, small y,
Yeah, 0 to y.
small y. Then you can the x distribution, that is 1 by 20.
Uniform 1 by 20 d. 0 to y or 4 to y? This is, I guess this is from
Sir, in the distribution that capital Y is equals to 4 when x is less than equals to 4. Small x if x is between 4 and 8.
4 and 8, right?
Yes.
So we are
So
replacing y with respect to x. Y is equals to x. So that means I am computing probability in between this interval.
yes, because when y is between small, like in the open interval 4 comma 8,
Yeah,
then it is
open
equals
interval.
to x.
Yeah, so that is why it will be from 4 to y.
Okay, it can be.
See, this particular y is actually 4 less than or equals to y less than or equals to, see, 4 less than or equals to capital Y less than or equals to small y, right, in this particular interval.
Yeah, yeah.
Uh, so that means probability that 4 less than or equals to x less than or equals to y. So you need to integrate from 4 to y 1 by 20 dx. So if we integrate that, we will get y by x by 20, which is y by 20 minus 4 by 20. Yes, correct. Correct. So the answer given looks like it is incorrect. So yeah, someone asked this question. Hello?
Yes,
Can
sir.
I get her? Yeah. So the distribution should be like this. The CDF should be given like this. So there will be a break Why we are including 4 here?
So,
Hmm?
is that the reason why they have added 4 by 20 along with y minus 4 by 20 in the range of y between 4 and 8?
No, did they add or?
It was like 4 by 20 plus y by 20 minus 4 by 20 in the range if y is between 4 and 8.
Okay.
So
Hmm.
what was the answer in 4 to 8?
Okay, they just added those two, is it?
So like 4 by 20
Yeah,
plus,
yeah.
then they have included the 4
4
first.
included. Yeah, correct. So we got between 4 to 8, we got y by 20 minus 4 by 20. They just wanted to combine these two and show it as a CDF. What they did is fy of y, they said 0, y is less than 4, and they combined it 4 to 8, and they took this and they added this both, 4 by 20 plus y by 20 minus 4 by 20, and this is like y by 20, y by 20 in between 4 to 8, and if it is greater than or equals to 8, y greater than or equals to 8, it will be 1. Okay, so yeah, actually you can split this interval like probability that y is equals to 4 plus from 4 to 8, like this. So you can actually do this, you can actually add those two. So that is what even they did in the answer they did.
Okay, sir. Thank you.
There should be equality symbol. Okay, so I think that is what you are confusing for. So for 4 less than y less than 8, they have given it should be like 4 less than or equals to y less than 8. Okay,
Yes, sir.
yeah. So then that will be y by 20. Okay, so yeah. So today
But
we will
sir,
discuss.
so in the previous one, you wrote y greater than equals to 8 1, but it is not coming from there, right?
See, y
Because
greater than
if
or equals to 8 is actually it covers all the values, right?
but
Yeah.
from the CDF, like y small y by 20, if you just replace with 8,
Small y by.
but so it will be a discontinuous, right?
It
The
will be
CDF is
discontinuous. Yeah, it will be discontinuous because there is a
okay.
probability that y is equals to 8 also.
Yes, that's why I'm confused. Okay, okay, sir.
There will be a discontinuity.
Okay.
Okay. Yeah. So, yeah. So what shall we do today? Today I got one suggestion that we have to revise week 7 again, not again. So, in last lecture, what all the things have you learned? Anyone? Why everyone are silent? Is stats to that difficult, or week 7 is that difficult?
So I couldn't attend the previous session. So if you just could summarize once, like
Okay. So those who have attended,
yeah.
Uh, so we did till 7.2.
7.2. Okay.
Yes, sir.
Okay. Tell me
Yes, sir. Yes, sir. We did up to week
week
7.2.
7.2. Okay. Okay.
So can we do more examples just than simple theory?
Okay. Sure.
Sir, may I ask a question, sir? related to, so not this, related to the extra week activity assignment. So that third assignment.
Extra activity, I'm not that sure about that extra activity. You need to ask someone.
No, sir, the problem is different. It is actually the week 0 activity third extra activity. Sir, it is saying that I'm waiting for third peer review, but there is no third peer review for me, and it is saying that as you don't have enough reviews for your peer, your course staff will grade you assignment. So, sir, that is still not graded, and sir, still I am getting 0 out of 100.
Yeah,
Okay.
yeah, same.
I think
It's
the
okay.
main
Like
thing-
it will
Yes,
be
sir.
graded
I am facing the
later.
same issue, sir.
Same. I think many people have the
Yeah,
same
yeah,
problem.
it's okay because I am also facing the same. It will be graded once all the like assignments are complete. Before the end term, I guess it will be graded.
Yeah.
No. It really demoralizes it unless at least we see some good scores. We have more into really putting a
Sir,
Yeah,
it is, sir,
because
it
the
is so.
peer review system, right?
See,
So
the
they
thing
have
is,
not reviewed.
right.
So
We
that's the
understand this.
problem.
Even we
Actually.
know, we came to know about this. Like, see, the thing is, we are actually assigning 3 people to the task to review,
Okay,
each one of us. But
okay,
many of the students are like, they are actually submitting their assignment, but they are not reviewing, peer
oh,
reviewing.
okay, okay, okay,
Yes,
okay.
yes,
Yeah,
because I
sir.
have
That
also
is the
seen some
problem.
assignments like that.
Yeah, so that is the problem happened, and we now we should step in and we should review some of your assignments.
Okay,
Sir,
sir.
I
So for those,
By the 7th of before the 7th of August, it will be done, na?
it will be done. It will be done.
sir, I think the peer-to-peer review is not yielding any fruitful result, because you know what is happening. Say for example, if file is not available for one of the reviewer, then it should not be available to all the 3 reviewers. Now. So one of the reviewer is giving 0 marks because file is not available,
Correct.
and other 2 are reviewing it. And how is it possible? So many people are complaining about it. I think
Correct.
institute will take a note of it.
Yeah, we even we had some negative feedback regarding this thing also. So I'm not sure about this completely. What is
But sir,
happening
like,
exactly?
sir, I think one of the course instructor, one of them said that that after the peer review is done, there is a second level of checking that goes on from your side, I guess.
See, that is what that one of the instructor will do. Okay, so
Okay.
he is Mayur. Mayur will do all these things. So he's the better person to answer this. Okay, so I'm not sure what is actually internally happening, what all the discussions are happening. I know some issues like this, like many students are not reviewing others papers. So many students have got only 2 reviews done and the other review is still pending. And this is one issue we have raised. They have raised it in the meetings. And other issue is the same issue, like few are giving zeros to some other without even looking, and that is not becoming correct review. So they are doing something internally, and hopefully we will get a better result out of it. Okay. So please wait until few days. So please wait for few days. And meanwhile, in between, there will be a session on this particular activity, extra activity session. So in that you can clear all your doubts and everything. Okay.
Okay, sir.
Can you start today's session?
Yeah.
Yeah.
So let us quickly revise that week 1 and 7.1 and 7.2 also. So we have studied IID samples, right? So x1, x2, x3, and so on. Xn is IID to x. What is this IID means? Independent identically distributed. Forget everything, huh? What is IID?
Identically and independent distributed.
Identically independent
Distributions.
Does it matter really? We tell it differently, independent, identically distributed.
that is the convention name we have given to
Okay.
IID. So you can call it whatever. you wanted to call. You can call DII, distribution which is identically independent. Okay, so this is the general convention we gave for which says that these particular random variables, which are x1, x2, x3, x4, all these random variables follow the same distribution which is followed by x, and also each x1 and x2, x3, these all are independent to each other. So x1 is independent to x2, x2 is independent to x3, likewise
So,
x1 is independent.
sir, over here, like x1, x2, x3, x4 till xn. So there has been n sampling has been done.
N samples has been collected.
From there, these are some numerical, some
Yeah.
results that, okay.
So see this sampling. So sampling is actually a method in which we choose a sample. So there is a random sample. So randomly collecting sample is the sampling method. So so I collect randomly some n samples out of an x distribution is what a sampling means. So sampling is actually a method. Sampling and sample. Sample is different from sampling. Sampling means it is a method, and sample means it's the sample collected from a population. So this x1, x2, x3, x4, xn is a sample. Xn is a sample collected out of this
So,
x.
I have a question over here. Like in the video, in the lectures, sir said that sampling is nothing but an instance of the sample. Like if there are like if I'm doing the first time I am collecting some, I'm doing a particular sample, then it is referred to as a sampling. It is just an instance of the samples. It was referred to in the first lecture, I guess.
Yeah. Okay, so that is how it is. Sir has mentioned, is it?
Yes, sir. Like it is said like an instance. Say I'm doing it n times, so there are n instances. N sampling is going on. So he said that later we will only talk about samples, not will not talk about sampling anymore. But just to have an understanding about what sampling is, it is just an instance.
Instance of samples.
Yes.
Uh, okay. Okay, let me look into this. But as far as I know, sampling means it's actually a method in which we choose the sample. So see, so I randomly choose some 10 samples out of X. So in how do I choose? Like first number I choose randomly, second number I choose. A set of 10 I have chosen, like let me say I am choosing a sample out of X where X follows Bernoulli. Let us take simple Bernoulli 0.5. So my sampling output or samples I collect is I am going to collect 10 random samples. So out of those 10 random samples, it is like first 5 are ones and last 5 are zeros. So this is how I collected my sample. So this particular collection is called as sampling. So this is how I collected sample.
So sir, sampling is the process of collecting samples.
Sample, yeah. So this is not randomly collected. I collected first five samples one, and next 5 samples as 0. I can do it like this, or I can randomly choose. I can
So here
randomly
each
generate.
is xi.
Yeah, each one of them are xi's. So this is x1, this is x2, x3, x4, x5, x6, x7, x8, x9, and x10. So each one of it is a sample. So this is first sample, second sample, third sample, fourth sample, fifth sample, sixth sample. Likewise, 10 samples I collected, in which first 5 samples are 1 and next 5 samples are zeros. So collecting like this is a sampling. This is one sampling. This is one way of sampling. And next sampling is like I can randomly pick, I can generate using spreadsheet or simulation, or I can use Python code or whatever. If I use Python code, or I randomly pick some 10 samples out of this X Bernoulli 0.5, it may come randomly like 1 0 1 1 0 0 1 1 1 0. Like this particular thing, randomly choosing this particular sample is called sampling. Okay, in order not to confuse more, I guess the professor has mentioned one particular instance is called sampling.
So what's the purpose of sampling though? Like to know about the distribution?
What's the purpose of
sampling?
See, purpose of sampling is just to study data. So you cannot study by taking all the data, right?
Right. So just to representative, just to show how representative it is of the entire data.
Correct. So we actually deal, if your data is like normally distributed, you have many data points. You wanted to study about the data, or you wanted to study about the whole data, it is very hard to study. So in order to study that, rather than studying that, we actually choose a samples out of it, some particular samples randomly we choose, and that particular samples, after we choose that, and we will look around that samples, and we will do what every statistical knowledge we apply on it, and we compute mean, median, mode, and everything. So in real life, what happens is you don't know the data. So you don't know exactly, you know the data, but you don't know what that follows, what the data follows. It won't be like the normal shape, or you cannot directly identify which distribution is your data following. So instead of taking all the data points and using these formulas, taking all the data points and finding the mean will be difficult. Finding median will be difficult. Not difficult, it takes more time to compute if you have more data points. So there are many methods of samplings. So there is a cluster sampling. Have you heard about clusters? Any these kind of terms?
Yes,
Yes, sir,
clusters.
heard about it, but
So random sampling, cluster sampling. See, these are methods of sampling. So how to choose your sample out of a population is what sampling means. How do you choose? So you divide. If you wanted to choose some, see, if you are a TV reporter and you wanted to ask what is the latest issue going on, so that Agnipath.
Yes.
Right. So whether PM Narendra Modi has taken the right step bringing this Agnipath into Agnipath or not is what you wanted to ask every person or few people. You cannot ask every person in India, right? How will you choose your sample? So which set of people will you ask? Will you just ask only the people who are in Kerala, and you leave rest of the country, and you will take the
No,
people
we should ask for entire country.
You should ask for entire country, but asking entire country, you need to travel every city.
It should be representative.
Highly populated.
It should be representative.
It should, yeah, actually the correct thing is it should actually, whatever the sample you are going to take, whatever the set of people you are going to take, that should actually represent the whole country. So that is how you should choose sample. So clustering will be good. Clustering sample will be good. So you choose some set of 10 people in Kerala, some set of 20 people in Uttar Pradesh, some set of 10-15 people in West Bengal, and some in Maharashtra, some people like this. Here few people, you divide it into clusters. You divide each India into clusters, and depending upon the cluster density, you choose the number of people you wanted to ask. And even the people you choose should be like, you shouldn't ask only the youngsters who are in between 17 to 21. So whoever is between 17 to 21, they all say this is the best initiative taken by PM Narendra Modi. Correct. So ultimately you will reach, everyone supports it, and you might say that this particular thing is correct, and everyone India is supporting this. So it should not be like that. You should choose wide variation in age, in gender. You should choose all these, and you should actually pick your sample that actually represents the population. So how do we choose this sample is called as sampling. So there will be many methods of sampling. So this is one way of I define sampling, but you just go back what professor said, you just go back to it. Even I will go through that video lecture again. I watched it way, it was like 2-3 semesters back. So even I forgot, I guess. So this is sampling. So I will try to get the in what intuition professor has mentioned sampling is an instance of sample. Okay. Right now you don't worry about sampling. What we require is sample. Hello.
Yeah, sir has taken this type of example as sampling that you are taking, sir.
Your voice is too low. Can you be a little louder?
Yeah, sir, can you hear me?
Sir
has taken this type of example as you are taking it as a sampling. And he called it sampling tool.
Sampling tool, yeah.
No, sampling.
Sampling.
Yeah.
Okay, then even I am saying that, right? So that is how.
What you were telling, sir has also told that as a sampling.
Okay. So maybe his intuition of saying that particular sampling is one instance of sample is something, I guess. So just go to the statements before and after the statement he used. Okay, we will get that his actual intuition. So I will look into it. But you don't need to worry about what sampling is of in our course right now. That is what sampling means, but it won't come in the future also. We only deal with samples. Samples are actually subsets of population. So from the whole data, sample is actually a subset of population. Okay. So now, how do we justify that this particular sample is a proper representative of the whole population? How do we justify? So whatever the sample I took, how do we justify our sample? So whatever the sample we choose, how do we justify our sample represents the data, represents the population? So for this, if you know,
how it represents the data.
How
it properly represents the data.
How do we justify this? Like we have taken a sample, but we need to justify that this sample is actually a proper sample that represents the population, or this is the way we should choose samples, some random samples, and it actually represents the population.
The amount of sample
Out of
the population, you need to take at least something around more than 40 or 50% of the population.
40 or 50%.
Sir, how close sample statistics are close to population parameters?
Correct. Right. So population have some parameters, right? Some parameters. See, this population will have mean. This will have variance.
Standard deviation.
Variance is square root of variance is nothing but standard deviation. So these are some parameters of this population data. So this will have something. So whatever our sample we choose, even this particular mean, variance, and all these things at least need to be closer to, see, this particular mean need to be closer to this particular mean, and this particular variance need to be closer to this particular variance. So variance no need to be closer to variance. Variance actually need to be very less. So as we sample more and more, our variance need to be very less and less.
Closer to distribution.
Yeah. So that we will see. So what this actually is, this should actually, our sample mean and variance, our parameters of sample should actually be very closer to the parameters of population.
Sir, I have a small doubt. If we know the parameters of population, then what is the need to calculate the parameters of samples?
See, this is how we actually. This is not that we apply this in real world. This is actually we are studying this data. Okay, if you know the population mean variance, how to choose the sample. If you don't know the population mean and variance also, once you know you have a population, and if you know how to choose your sample, in which once we take that we know mean and variance. See, this particular mean and variance, if it is unknown, we take it as mu and sigma square, something like this, which are unknown. And with respect to this mu and sigma square, we choose our sample. And after choosing our sample, we actually compute what all the mean, variance and everything. We choose some random samples out of this unknown population. And our mean will be closer to some value. And our variance will become closer and closer to 0. And whatever this particular mean will be closer to, that will be the actual mean mu. So this is like an, what we say, first we treat like we know everything, and we take one sample out of it. We study on that, and using that study, we actually generalize it to the population.
So, sir, it's just to check the sanctity of the given data.
No. We don't know the mean and variance in real life. In real life, big data, you don't know what actually how the data is distributed.
So we have to do everything on
if
our
you
own.
don't if you don't know, what we do is we take it as a unknown parameters. So we will study this in week 8. See, if you don't know the parameters, we actually estimate our parameters. See, that is what we do in week 8. But in order to understand how we estimate parameters, we should know how we should choose our samples. If you know, at least if you know the parameters, how should you choose the sample? Later we will study if you don't know the population mean and variance, even then we can take some random sample and we actually estimate your parameter, and we can actually get to mu and sigma square. We can actually predict, or we can actually come closer. We can actually find the closure value of mu and closure value of sigma square. So this is what we do.
Yeah. Yes, sir. It's like true. And when we estimate, suppose a crops of India, I mean wheat. If we want to estimate the, how much wheat we are going to produce in this year, we obviously do not know we are not going to count everything, right, sir?
Correct.
We will devise some sample method, and then we'll extrapolate or whatever we do, and we find the actual population.
See, this is what we do. We start from here. What we start is we take one population which we know the mean, variance, which we know. So whatever we have right now, we have many data in which our population mean and variance is known. And if this is given to us, we actually generate samples out of it, and we actually study these samples. So in order to study these samples, one sampling is not enough. So one sampling, if you are done one sampling, like 10 samples you have collected, and if you study on that particular sample itself, it may not represent the whole population. What we do is we again do another sampling, maybe y x11, x12, and so on, x1.
Sample size remains the same, sir. Like 10 object I picked up in first sampling, so in second also I will pick up 10 samples.
So by taking these samples, this we know, population we know, by taking these samples, what we actually get is this particular samples, actually the parameters of these samples are very much nearer to the population parameters, is what our conclusion will be. Our conclusion. And later what we do is we actually collect few samples which from the unknown population, and using that samples we actually predict population parameters. So see, this is what in as a data scientist we should do. So you have to study from the past data and use the techniques of statistics, and you have to predict the future. So right now we are in the studying process. So we are just studying if I know the population mu, sigma square and everything, how should I collect my samples, and after collecting my samples, how my mean variance, we are just looking how my mean variance are of these samples closely related to this population parameters. We are studying this, and these things we will apply on the unknown population thing. Okay.
Yes, sir.
Got the point?
Okay, sir. It means that examples used in slide is just for studying purpose.
Studying purpose.
Yeah.
So understanding purpose. So how these samples means and the population mean are closely related. How these are related. Without samples, that is why we take samples as random variables also. We don't say, we don't pick one sampling. We pick x1, x2 and so on, some x10, where this x1 is actually a random sample. So we don't know the value of this. This is actually random variables. All these are random variables. So this will actually cover all the samples. We are not picking one sampling here. We are actually collecting all the samplings. And we are talking about...
We collect different samples and try to visualize where is the parameter stands to. That should be the real parameters of
that should be the real parameters. That is how we understand. Okay. Later we understand the things. Then what we do is you go for a population which you don't know the parameters. You actually randomly pick some samples out of it, and you know that your random sample parameters are somewhere nearer to your population parameters. Then we will estimate our parameters. That is what we are going to do in week 9.
Okay, sir, got it.
Okay. Yeah. So now let us take some random samples and random samples, which are IIDX. So again, let us take example kind of thing only. So let me say X is binomial 6 or 5 comma 1 by 6. Okay, binomial 6 comma 1 by 6. Ten comma 1 by 6. Okay. Okay. What this actually is? This particular X is binomially distributed. So X can take 11 values, right?
10 values, sir. N equal to 10.
N equal to 10.
And P 1 by 6.
10C0 to 10C10.
10C0 to 10C10, right? 0 also counts, right?
Yes.
So what is the range of X?
0 to 10.
So it can take 11 values.
Yes.
Correct? Yeah. So now X1 is actually a random sample chosen from X. In this distribution, chosen from this distribution. X2, that means X1 also follows binomial 10 comma 1 by 6. That means X1, range of X1 is also from 0 to 10. Okay, 10 is a bit confusing. Let us take till 9. Okay. So not only X1, Xi's follow binomial 9 comma 1 by 6, where each and every range of these random variables are from 0 to 9. Now, if I wanted to look at the sample mean, so this is the sample. Sample mean is simple, which is you just add all the values and divide it by number of samples you have. So this will be the sample mean, right?
Sir?
Correct?
Sir? When we say sample mean, basically it is the mean of the means of all the samples, right? We have taken 10 different sampling, na? 10 different
10
sampling.
different samples.
Achha, 10 different samples, okay.
Yeah. So we are actually saying sample mean. So samples ka mean. So whatever, how many samples I have? 7 samples, n samples
Sir,
I have.
in each sample, how many things are there, sir? In each sample, 9 x's are there, no?
In each sample, see this particular x1 is unique. It will take one sample, one value. Just like, see this particular, let me say, I have chosen one sample, which is like 1.
Sir,
8,
in capital
7.
X, small x samples are there, sir, in this one.
In capital X?
No, x1 is a random variable like x1, so which takes in the range of 0 to 9, right?
X1 is actually identically distributed like X. That's it.
Yes. So suppose I am doing a suppose I am doing I am taking a sample. So say then x1 represents that sample, like for then x2 represents the second sample, like that.
Sir,
like when you are taking x1 x2 to xn, this IID this distribution to IID x, then can I say that there are n samples have been done?
And samples of X
has been taken from there x1 x2.
Yeah.
Okay.
Sir, एक बार ऊपर जाएगा सर, ऊपर already explain किया ना वो. ये stop sir. This one 1 1 is 0 0 up to x10. This is this totally called as one sample, na?
No. These are 10 samples taken from X. So X takes value 0 1, either 0 or 1, right?
Right.
With probability 0.5. Right?
Right.
So random, not randomly, as this is X and distributed Bernoulli. So I have experimented and I have taken one output, one sample. So I have done one experiment and my output value is 1. So that is x1. So x1 is nothing but it is the first time. So okay, let us consider it as a coin toss experiment I am doing. Okay, coin toss experiment is like if it is tail it is 0, if it is head it is 1. So this experiment, first time I have tossed the coin and it was turned out to be head. So that is x1. So first coin toss is the random variable x1. Second coin toss is the sample x2. Third toss is the sample x3. So these are 10 times I have tossed my coin and I have got 5 heads in the first 5 times and 5 tails in the next 5 times. So these are 10 samples. Here sample means, in our case, whatever the example we are, one sample means one time coin toss. Did you get
it? Right. In total experiment, there are 10 samples. That each point is one sample.
Each is one coin toss. We have done 10 coin tosses. So for one toss, we get one sample. For 10 tosses, we get 10 samples. And these 10 samples is collectively called sampling. So this is how we done sampling by collecting 10 samples out of X.
Okay. Right.
Yeah. As this is Bernoulli, this has only 2 values. What if your X is normally distributed? Normal
0, 1.
Okay, 0, 1. Even if it is standard normally distributed, your X can take all the values, right? Any value from minus infinity to plus infinity.
Yes, sir.
Yes.
So if I have done randomly I have chosen one point. It may turn out to be, first sampling may turn out to be 0.01, and the second sample is nothing but I am choosing one, I am doing one experiment, and for that experiment I am getting value of x as something. So as this is normally distributed, I randomly choose one value to x. So that particular x will be the first sample. So 0.12, 0.13. So yeah, it's better to show on Google Docs, I guess. Correct? So it will give me random samples. Just a second, okay? Let me open Google Docs. Okay. Is this visible?
Yes,
Yeah,
sir.
sir.
Yes, sir.
Okay. Now you see, if I type something like ran between 1 to 20. So what am I doing is, I am randomly choosing. So let us say my x is uniform. My x is uniform 1 2 3 to 20. Okay, so this is different. This is not continuous distribution. This is a discrete distribution where x takes values 1 2 3 to 20.
Right.
So this is one sample. Okay, I randomly experiment. I am taking one value of x randomly between 1 to 20, and 16 I got as my first sample. And if I wanted to take some 10 samples, you see, this is the first x1. This will be the x1 for me. This is x1 and this is x2. So values will keep on changing. So as we have typed rand between integers. So yeah, so like this.
So, sir, like when we see in a data, like in a Excel sheet, when you see that, suppose
Hmm.
there is a data on height of person. So in the column of the height, so those values, those are individual xis.
Individual x size. So randomly you don't know which person will come and what is his height.
Okay.
Correct. So that will be one sample. So one person height
So
is one sample for you.
so the number of cases that have, like the number of rows you have, those are the number of times the samples have been done. Like those are the total number of samples.
So those are the total number of samples I wanted to take. I wanted to study.
Okay.
Okay. So I just wanted to take only 10 samples. So okay, we are in a class and we just wanted to measure the average height of the people in the class. But the class is of some 2,000, 3,000 people. So I cannot each, and even 3,000 is simpler. So okay, there is one PM Narendra Modi meeting is happening and maybe some 3 lakhs have attended that meeting. Out of those
Yeah.
3 lakhs, I just wanted to compute the average height.
Yeah.
I don't want to take all the 3 lakh people height and add all the values of 3 lakh values and divide it by 3 lakh and say this is the average. I just don't want to do that. So what I will do is, so I will randomly take some sample out of it. Maybe out of this 3 lakh, I will take some 3,000 people sample. So 3,000 samples is I am taking those 3,000 samples. Okay. So there will be some 3,000 rows, and each person is a sample for me. The height of each person is a sample for me. Okay. Even here also, we actually taken this 8, 8, 6, 13, 7, 4, 16, 10, 8, 12. These are all samples taken from this X uniform 1 to 20. So X is a random variable that can take values between 1 to 20. I don't know which value it takes. If I take one random value suddenly, my first sample, if I perform my experiment, my first sample, I got it as 8. So my X is taking value 8 for the first time. And the next time also it is taking value 8. But in the third trial, it took the value 6, and later it took 13, 7, 4, 16, 10, 8, 12. So if I compute the average is somewhere around 11.7. But this is one sampling out. I took, this is the one sampling, right? I have taken some 10 samples, and this is only one sampling. Likewise, I can actually take one more 10 samples. So one more 10 samples. Okay, no need to one more 10 samples. Here only it is giving me. See this particular thing, you see. So these are okay, you see, each time I change, these values keep on changing. These random samples keep on changing. Each time it changes, it is like a sampling, one set of sampling. Likewise, if I keep on changing, I will get something like 11.2 this time. Later I am getting 10.7. Later I will get something like, okay, I'm getting 10.7. Okay, let's say 8.9, 9.9. You see these values, 9.9, 8.9. So these are pretty much nearer to 10, right? So 13.6, 11.1, 10.8, 8.8, 9.8. So these are different set of samplings. And if I unionly see these samplings mean this distribution actually. So sample mean is actually a random variable for me. Correct? So even the 11th one is also keeps on changing, right? It is not constant each time.
So can you once talk about the empirical distribution with using this, like what exactly is doing?
See,
sir, 1 minute, sir. Let to complete this. Actually, x1 to x10, these are the values which it is getting changed, and mean is getting changed every time, and every mean which it is changing, we are calling as a sample, na?
Every mean is actually the sample mean of one particular sampling. Okay, so this 12.3 is sample mean of one particular 10 samples. These particular 10 samples ka sample mean is 12.3. Okay, what this actually 12.3 means is it just added all these 10 values and divided it by 10, and it is 12.3. And one more 10 samples I have taken, and the sample mean here became 9.5.
Okay, right.
Okay. Likewise, what we do is we actually randomly pick some 10 samples and look at the mean. So each time I look at the mean, even the mean varies. Mean is not constant.
Correct. Yes.
Mean is also a random variable for us.
Yes.
So if mean is a random variable, then even the mean has some parameters, like even the mean contains mean. Even the mean has mean, and even the mean has variance.
Yes.
Like we don't say mean, expected value or mean, both are same, right? Even now mean is a random variable. Mean has some expected value and mean has some variance. Correct?
So that's what I was asking, sir.
Right.
That's what I was asking, sir. Mean of all the means of all the sample we call sampling mean, right?
Sampling mean.
Or sample mean. Sorry, sample mean.
Sample mean. Yeah.
Sir, it will not take more than 1 minute, sir. The way you have generated one sample, na, sir. If you copy it and paste it as a value, then it will not fluctuate, sir, right? So if you make You copy it. Input average also, sir. Input average also. Yes. Copy. No. Okay, yeah, you can generate it. And now paste it as a value. So now it will make our study more interesting. So we will have 10 sampling in front of our head. Then we can discuss all the,
Okay.
It will make our study more interesting, sir, and will bring more clarity, sir.
Okay, you see.
Already we have generated 6, so we can generate like 10. Yeah, 4 more. 4 more. Yeah. Okay, now so many are there. Yeah, 3,
Okay.
4,
We
5,
can
6,
generate.
7, 8,
Now
9,
you see,
10.
this is 10 samples, one set of 10 samples. Okay. So let's start from here. So you see this, the sample mean of these 10 samples is 10.3. The sample mean of these 10 samples is 9.1. 10.4, 12, 12.5, 11.1, 10.6, 10, 10.5, 7.8, 11.8, 12.2, 9.9. Even this mean is also a random variable. X1, X2 and so on, Xn, X10 are random variables. And this particular X bar is the mean, which is actually a random variable, and it is equal to X1 plus X2 plus X3 and so on, X10 divided by 10. Correct?
Yes.
Now this X bar, what we are seeing is actually varying. So this is a random variable. So as this is a random variable, this random variable will have some expectation, expected value, and this particular random variable will have some variance. Correct?
Yes.
Yes, sir.
So the expected value of this sample mean will be the mean of actual distribution. So what is the mean of this X is uniform 1 to 20?
10.5.
20 minus 1 by 2.
No, sir. A plus
Correct?
B, A plus B by 2.
A plus B by
10.5.
Okay, 10.5. A plus B by 2.
Yeah, 10 plus.
So it is 20 plus 1 by 2, which is 10.5.
Yes.
So actual mean is 10.5. Correct? So even if you see this, we have generated some n and n minus 1, 13, 12 samples. 13 samples. Correct? Some 13 samples we have here. 13 different 10 set of samples. So we say 13 samplings. Okay. So let us use the convention what professor has used.
Yes.
So let us call it each of it as a sampling. Now we have 13 samplings with us. And each sampling contains 10 samples inside it. So out of this 13 samplings, we have 13.2, 10.4, 12.2, 8.6, 8.8, 7.5, 7.4, 10.3, 11.1, like this. So these values are pretty much closer to 10.5. Correct? So few values are greater, few values are lesser. And if we compute the mean of these means, we will get somewhere around, okay, we will do that thing also. So what we do is, we sum, okay, average over average C11 to C14. Sorry, not C14. And 11. Okay. You see, out of this 13 samplings, we got 11.11 as the mean of sample mean. Okay.
Sir, what's the actual mean?
Actual mean is 10.5.
No, sir. What is this? It will means of all random variables.
Means of?
All random variables.
Yes. 11.83 is the mean of all the means.
11.18 is mean of all these sample means.
And the 10.5?
And 10.5 is the actual population mean. Like, not population mean, X is uniform between 1 to 20, right? If X is uniform between 1 to 20, what will be the expected value of X?
Okay.
So that is 10.5. So like this, if we use more and more samplings, If you use few more samplings, this 11.18 will be something like 10.95 or something. If you use still more samplings, it will actually be will come closer and closer to actual mean, which is 10.5. Okay, so the expected value of this mean, this sample mean, will be same actual mean itself, and the variance of this sample mean will be sigma square by n. Why this variance of this sample mean is sigma square by n? Why divided by n? Okay, see, if we take more and more samples at a time, so I took only 10 samples each time. If I took some 100 samples at a time, where will be my expected value of mean be?
Very close to 10.5.
More nearer to
Pretty
10.5.
pretty close to 10.5.
Yes, more close to 10.5. Yes.
When it is
Spread
pretty
decreases.
so all the values will take pretty closer to 10.5. Okay, let me so we have randomly generated few. Okay, these many. You see now, how are these sample means now? 11.58, 12, 9.10, 11.9, 9, 11, 10,
You
11,
need to
10.
take mean of all these means.
See, these are pretty much nearer to 10.5 than these values. See, there are some 8.1s here, 8.4s here, which are very far from actual mean. But if I increase my samples, number of samples, my mean is very much, it is actually 9.66. 9.5 is the least one and 12.12 is the highest one. If I compute mean of these samples, if I see the variance of, if I see the variance, what is variance actually? So how far is it distributed? How far each value is distributed? So the distance between these points are very closer compared to the above ones. Right? There is 7.1, there is 8.1. The distribution is quite wider. So we have 7.1, 8.1, 11.9, 12.3, 13.1, 13. So this has from 7.1 to 13.1. So which is a like 6 interval. So the data is distributed in that 6 interval, 7 to 13 interval. So the variance will be high compared to this particular variance, the variance of these samples. And if I increase more number of samples each time in the sampling, my mean will be, all the sampling means will be get closer and closer to 10.5, which tells me that the variance of this sample mean will come closer and closer to 0. So the variance of sample mean will come to 0 if I increase number of samples. Okay.
That's the reason why it is divided by n, sigma square by n. Right?
Sigma square by n. So if I keep on increase my n, the number of samples, my variance of this mean values, see this variance of this mean values.
So let us compute the mean of all these means on the right hand side. Yes.
See, what you will get?
Very close to 10 point. Yes. 10.5.
Average of C59 to N59. So see, this is like 10.08. Okay. So what is this? 10.708. This is luckily happened. Okay, don't be like this has given the better.
That keeps changing, sir. That is the reason why it is happening.
Sir, actually, we are also interested in variance, not really
About
the
mean, is it? Variance of C 59 to N59. So what is the variance here? 0.81. Let us compute the variance here. Variance of C11 to N11. See, the variance is actually 4.468 something. Here the variance is somewhere around 0.977. Correct? Okay, can you see the difference?
Yes, sir.
So the variance is lesser than this variance because our number of samples we took each time is lesser. So mean will be widely distributed. Sample mean will be widely distributed when compared to this sample means. If I increase n, your mean will come closer and closer to 10.5 and this particular variance will go to 0.
Sir?
Okay. Yeah.
I think here we have taken 20 samples in this sampling, right?
20
Almost.
or more than 20.
More than 20. Okay, let us take
20 to 55.
35, right?
Like 35 samples.
35. And how many sampling we have done, sir? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 we have done, right, sir?
12.
So while computing the value of n, we will write 35 or 35 into 12. What we should write, sir?
While computing?
Sigma square by
here
n.
value of n is something like this 35.
35, okay.
Yeah. Okay. So we are only doing one set of sampling. Okay, every time we do one set of samples, we collect only n samples. So these many things will not happen. We only
while we have calculated 0.97, sir, so we have taken into consideration all the samplings, right?
All the samplings means I am just showing you.
Yes, sir.
How this mean actual mean. These are actually we are taking a random values.
Correct.
We are giving the values.
Okay, got it. So the value of a small n will be 35, not 420.
Not 420. Yeah.
So in case of this variance, it will be 12, no, sir?
In case of?
This variance, this sigma square, it will n will be 12, no?
Where? No.
Here, 0.97.
35, 30. This particular n 0.977 is like 12. We have
12,
taken
no?
only these 12. Yeah.
Yes.
So this 0.97 is the variance of the sample mean.
The variance of the sample mean. It's not sigma square by n. It's like it will compute the mean. This 10.74 minus 10.62 whole square, 10.87 minus 10.62 whole square. So this minus mean whole square, this minus mean whole square, this minus, and so on, divided by n minus 1 is the variance. We know how to compute variance, right?
Yes, yes.
Pardon me, sir. While calculating, what's the formula for sample variance of mean?
See, formula we have is sigma square by n. If you know the population variance, you can directly compute.
So we have like the population variance, but here like we should say that 0.977 divided by 35.
See, this 0.977 is not the variance of the population.
No, I'm sorry. My mistake is that like sigma square divided by n should give me 9.7 to 0.977 here. Rather, sigma square divided by 35 should give me 0.977. Is that what it's coming down to?
No.
Can you please explain this part?
Yeah. So what is the variance? Population variance?
Sigma square.
What is sigma square?
X minus x bar whole square, summation of that divided by n minus 1.
X minus?
X minus
No,
X.
if X is uniform between 1
Okay, okay,
and
then
2,
it is
what is
B minus A whole square by 12, something
2?
like that.
12, yeah.
Yeah,
Yeah,
yes.
B minus
So
A whole
19
square.
square by 12.
Yes.
Correct? What is 19 square? 361. 361 by 12. 30.0833. Okay. So this is the variance of actual population. Okay. Now, whatever the variance I have computed here, this particular variance is actually considering these particular values as my random samples, and these random samples mean is 10.004, 10.6004, and once if I know the mean and if I know the sample actual data sampling data, how do I compute variance? So each point is this, each data is this, and I know the mean of this data. So in order to compute the variance, I have to subtract each data with my mean and square it and
Find a
add
standard
all those
deviation.
things. Yeah, and add all those things and divide it by n minus 1
Yeah.
is the sample variance. So
Yes.
this is the sample variance. So in order to show you that this particular variance will go to 0 as we keep on increasing the value of n, that is why I took these many samplings of 35 samples each. Okay. So usually this sigma square by n works out to be, if this is your 35 samples, now the sample mean is 10.871 and the sample sample variance is 30.0833 divided by 35 is your sample variance. Understood? For this particular sampling. Likewise, the second sampling, this particular sampling consists of 35 samples, has sample mean as 9.56, which is
Sir,
expected value.
sir, shouldn't we find the variance for each sampling independently?
Shouldn't we find
The sample variance of each sampling?
each sampling sample variance?
Yes, sir.
So that is other case, right? That is S square. Sample variance is different. We are only worrying about, right now we are worrying about sample mean ka expected value and sample mean ka variance.
Sample mean variance we are.
Yeah, sample mean variance and sample mean expected value.
We are not talking about sample variance
till
yet.
now we didn't start talking about sample variance yet.
Okay, okay, sir.
Okay.
Okay.
So these are some samples. In order to show you that actually the expected value of this sample mean goes nearer to 10.5, which is the actual mean, and the variance of this sample mean will come closer and closer to 0 when my n is very large. So if my n is 35 here, n is 35 here, I have 10.87 as 87 as one sample mean, other sample mean, other sample mean. Like this, I have some 12 sample means with me. If I compute variance of this sample means, I got 0.679. If I had increased few more samplings or few more n's, like some 50 samples I have taken each time, my mean will be somewhere very much closer to 10.5 each time. And if I compute the variance at that particular time, my variance will be lot more closer to 0, and that is how I can say that as I keep on increasing my samples, my sample mean variance will come closer and closer to 0. So from here we deduce that formula sigma square by n by studying this much data, not this much data. This is 0.001% of the data we studied. So likewise, they studied whole data of this uniform 1 to 20, this uniform 1 to 20, and they have collected many samples like this with n being very large, and they have computed the sample mean for each and every time. Their value is very much closer to 10.6, 10.7, 10.4, 10.2. So you keep on, now you do it, take it like an experiment. Now till now I have taken 35, right? 35 is the maximum I took. Now you take n as 100. You generate some 100 samples, 100 random samples out of this x uniform 1 to 20. And you just compute the mean of that random samples. Consider it as one sampling. You just take few more samplings like this, and you just see the mean of those samplings. All the sampling means will be very much closer to 10.5. If the sample mean is very much, all the sample means are very much closer to 10.5, then the variance means how far each sample mean is placed. So if everything is very closer and closer, our variance will also be very much closer to 0.
It will converge to 0.
Yeah. So after studying all this data, they have come up with these formulas stating that expected value of our sample mean will be the same actual mean itself, and the variance of this sample mean will be sigma square by n.
So the variance that you wrote in the that you calculated is 0. That one. So that is very near to 30 by 35. If I do like the variance, population variance by 35.
It will be very much nearer to 30.30 by 35.
Because it is coming around 0.8 something.
Yeah. So it will be very much nearer. See, these are actual data sets, right? It won't actually follow the population, follow the formulas. See, this is one small data we have taken.
Yeah, like I'm asking, it is approaching to that.
Correct.
Yeah. Okay.
Right. So yeah. So this is about this sample ka expected value and sample mean ka expected value, sample mean variance. Now, if I wanted to look at the sample variance, so that means I have taken some random sample, and how do I compute sample variance? So this is like
sample variance is just in sigma square.
Sample variance is?
Because variance, each xi follows has a variance of 30 point that. So if I am talking about sample variance, then there are say there are 10 samples, so 10 uniformly distributed random variables, identical, like independent. So I can just add them.
This is not sum of 10 random variables, right? You are talking about the variance of x1 plus x2 plus x3 and so on x10. So that is not we are actually talking. We are actually talking about the sample variance. So I randomly took some 10 samples out of this x uniform 1 to 20. And once I got the 10 samples, what will be the sample variance? How far all the 10 points are distributed?
Okay, so within those 10 values, the variance sample.
Yeah, within the 10 points, we compute the variance. How do we compute? This minus the mean whole square, this minus mean whole square, this minus mean whole square, like this, right? And divided by n minus 1. So that will be the sample variance. Now, once I get the sample variance, what is the sample variance parameter is actually how this is related to my actual population variance. So it turns out to be the expected value. Yeah.
So sample variance is also a random variable.
Yeah, sample variance will also be a random variable. So let me show you that where variance C1 to C10. Okay. So this is 36. Likewise, we have now we have 48.5, 30, 17, 50, like this. So what is the expected value? Expected value is nothing but the average of this. Average of C12, 2 and 12.
Expected value of sample variance.
Yeah, expected value of sample variance. So you see expected value of sample variance is 34.901. So somewhere nearer to 30. It is not equal to 30, but somewhere nearer to 30.
Right.
Right?
Nearer to original variance of this.
Yeah, similar variance, nearer to. Why this is this much difference is because of we have taken only some 10 samples each time. So what if my number of samples are very high? So this is where of C C22, C59. Okay, this is 34 point something. Okay. And these are the sample variances of each time we sampling. See, these are our data we are actually studying. We have considered this 35 samples one time, 35 samples other time, 35 samples some other time. Like this, we have considered some 12 samplings. You can go for 13, 14, 15. You can look for this. And ultimately, we get the expected value will be, sorry, average of some C62 and 60. See, if my number of values are high, number of samples I take each time are high, we got 30.861 as my expected value. That means mean of my sample variance as 30.86 is somewhere very much closer to 30.083, which is the actual population variance. So if you enlarge your data and if you take more samplings, more number of samples each time, so by taking all these things, they actually computed that. So scientists actually computed that expected value of this sample variance will be equal to population variance. Okay.
Yes. So that's what we calculated. That was the variance of each sampling, right?
Each sample variance.
Yes, variance of this one 30.861. This is
the
nothing.
mean of these sample variances.
Yes, mean of all the sample variances, right?
Mean of all the sample variances. That is expected value of all the sample variances.
Yes.
Okay. So these are the data we took. That is why we got 30.861.
So with the help, sir, with the help of this 30.861, we infer about variance of population, right?
We infer about variance of population. That is what. See.
Correct. And sir, with the mean, with this mean of sample means, we infer about the population mean, right?
Population mean, yeah.
But then, sir, what is the practical utility of variance of sample mean? Like that's what we calculated for sigma square by n. So what is the practical utility of that?
Practical ability of that is actually whatever the samples you are choosing is actually you are choosing the correct representation of your population.
Correct, that's fine. Not. But if I take mean of all those means, I will reach very close to my population mean, right?
Similarly, you will reach
very close.
Your data might very good, right? While you are reaching that, even then it is good to see, it is good to understand how your sample means are varying.
Okay. So that's the practical utility.
Yeah.
Okay.
So how far other things are there? See, is your sample mean coming one as 10 and other as 20? And if you take the one as 0 and other as 20, if you take the sample mean, it will come up to 10.5, which is actually the actual mean. But are those particular data which I choose as which gives me mean as 0 and mean as 20 is the correct data I should take, or I should take the better data?
Got it, sir. That is the reason why we study variance of all the sample means also, right?
Yeah.
Got it, sir. Thank you.
Yeah. So this is sample variance, sample mean, and everything.
And this we called expected value of variance of
Just,
got it, sir.
yeah. So this is how we understand the parameters of samples with respect to the population parameters. Now that if we know population mean, variance, and everything, actually we can collect some samples, and we know that the mean of those samples, sample mean, will be something x1 plus x2 plus xn by n, but expected value of the sample mean will be the expected value of the population, and the expected value of the sample variance is actually the population variance. So these are the derivations which we derive from the actual data which we know. After deriving this, we will use this for unknown population things, unknown population parameters. We will use this sample expected value of the sample means. We collect random samples, we compute the means of each time samples, we collect random samplings. For each sampling we compute the mean, and we do iterations. We Monte Carlo simulations. Have you heard of this name, Monte Carlo? So this actually generates each time it generates randomly samples, and each sample mean we will collect, and we will look at the expected value of this sample mean, and we will, of the value which we get, we actually predict that this particular value is actually the mean of the total population. So that is how we study, we use it in future. Okay. Okay, this is one thing.
This is one and two are covered, sir.
Yeah, this need to be understood. You should take some time and you should understand these things. And I think other things are very easy.
So week 3, lecture number 3 and 4, we are talking about such NGF and all, sir. So, and that was not covered, last session.
Yeah,
last
NGF,
session, last session we had covered only up to lecture 2.
Okay.
So 4 and that lecture number 5 are.
Lecture 4, we will directly shift to lecture 4. I don't think lecture 7.2 has much thing to discuss. So it has some.
It's all about data.
Sorry, whatever we discussed is about 7.2 only, I guess.
Yeah, 7.1 and 7.2 are done. I'm saying 7.4 and 7.5. 5 means that additional lecture.
Okay, let us complete it very quick. So in 7.4 we have the sum. We will talk about the sum of the random variables. So let us say x1, x2, xn are in random variables, and the sum of these random variables is nothing but x1 plus x2 plus and so on plus xn. So this is the sum of random variables. Now we know expected value of this sum is using the linearity of expectation. This will be expected value of x1 plus expected value of x2 plus and so on plus expected value of xn. So do you guys remember the linearity of expectation?
Yes.
What it says, expected value of x plus y is
expected value of x plus expected value of
expected value of y, and expected value of a times x is
it will come out a into expected value of x.
And yeah, and we have few properties with variance also. Variance of a times x will be a square square of x. And what else? Yeah, variance of a constant is 0. So variance of a times x plus b will be a square variance of x only. Okay, so these are some linearity of expectation and some properties of variance. So using that we get the expected value of the sum of random variables is equal to the each of the expectations sum. And also we can talk about variance if these x1, x2 and so on xn are IIDs. So no need to be identically distributed, but it should be independent to each other. If these are independent to each other, then we can talk about the variance of S. So variance of this sum, which will be each of the variances. variance of x1 plus variance of x2 plus and so on plus variance of xn. So this is what. So there is no linearity of variance if those two random variables are correlated.
Sir?
So what is correlated means?
Both of them are varying in the same direction or not?
Both of them are
varying in the same direction or not?
So if there is a correlation, that means there is a covariance. So if there is a covariance, then those are not independent. So if they are not independent, we cannot write variance of x plus y as variance of x plus variance of y. So that is not allowed.
Sir, in this only we are discussing only on sum. Why on subtraction that we didn't discuss?
Subtraction is just the inverse of addition, right?
So covariance is a weaker condition than independence, right? Like independence implies covariance is equals to 0. But not the vice versa, like not the other way around.
Independence implies correct. So there can be few random variables which satisfy
like which are not
value
linear.
of x. Yeah.
It can be.
Sir, one small clarification, sir. While we are adding s equal to x1 plus x2 plus xn, so here x1 is the mean of my each sampling, right? So x1 is the mean of my first sampling, x2 is the, if I correlate, if I try to understand with respect to what we discussed so far. So x1 is the mean of sampling 1, x2 is the mean of sampling 2.
No. See. Here we didn't tell that these are IIDs of some random variable x.
Okay.
See, these are some. This is something new topic now. So we are just actually talking
I'm just
about.
trying to strike a relation.
No, there is no relation. Don't strike. So this is actually we are talking about sum of random variables. We are just trying to look at sum of few random variables. See, this x1, x2, xn are some random variables, which are we didn't said that not necessary that these need to be IIDs of same x. So this may follow something Bernoulli, this may follow something binomial, and this may follow something Poisson. That other one may follow geometric. We never said that these should be identically distributed. If I have some random variables like this, if I wanted to look at the sum of these random variables, that sum of random variable ka parameters, how will the parameters of that sum of random variables will be associated with this each of the parameters? Like expected value of s will be expected value of this, sum of expected values of each of the random variables, and if these are independent to each other, then the variance of s will be the sum of variances of each of the random variables. Okay, we didn't bring IIDs into the picture yet. We are talking about some random variables. Each of them are different random variables. We will bring that the IIDs very soon, then we can correlate.
Got it, sir. Thank you.
Okay. Yeah. So till now we discussed this, and we can see some properties of how those are derived. Like whatever the just now we studied, right? Expected value of sample mean is mu population mean. Variance of sample mean is sigma square by n, and what are the other? Expected value of sample variance is sigma square. So we will see that here. So before that, we need to understand about the scaling. What is scaling? So if I have some random variable ss, something like a1, some coefficient multiplied with some random variable x1, and a2 with x2, and so on, plus an with xn. Okay. Now, what is the expected value of s? So we use the linearity concept itself. So expected value of a1 times x1 plus expected value of a2 times x2, and so on. So this will be like a1 times expected value of x1 plus a2 times expected value of x2 and so on plus an times expected value of xn. And variance of s will be, so let us say x1 and x2 xn are independent to each other. So variance of s will be a1 square times variance of s plus a2 square variance of s, like this, plus an square variance of s.
X1, X2, no?
Sorry. x1, x2, xn. Yeah, the time is 9:50, right? So it happens.
Lot to cover, sir.
Huh?
Nothing. Lot to cover.
Not to?
Lot to cover. Lot to cover.
Yeah, lot to cover. But what am I saying is I am writing s instead of x1. That happens as the time passed 9:45. Okay. Now let me introduce that IID here. What if my x1, x2, xn, all this follow some IID x, where this x has parameters, so expected value of x is mu and variance of x is sigma square. Now what happens to my expected value of s? So this is something like a1 times mu plus a2 times mu. So this x1 and x2, everything will have expected value mu. So these are our IIDs x. So whatever the parameters x has, the same parameters x1, x2 and so on xn will have. So therefore the expected value of x1 is mu, x2 is mu plus and so on plus an times mu. This will be like a1 plus and so on an times mu. And what is the variance of s? This will also be like a1 square plus a2 square plus and so on an square of sigma square. So till now we are okay with it, everything. So sum we know. Now let us look at x bar, which is a sample mean. So x bar is equal to x1 plus x2 plus and so on xn by n, correct? So this x bar is nothing but the scaled sum of each of the random variable. Where a1, a2, a3 and so on ans are nothing but 1 by n here. So all ai's are 1 by n. So now if I look at the expected value of x bar, this will be 1 by n plus 1 by n plus and so on 1 by n times mu. So directly I am substituting here. So a1 plus a2 plus an, all a1, a2, a3s are 1 by n's here. So if we do so, we will get n by n times mu, which is mu. Okay. So therefore expected value of mu x bar sample mean will be mu. So similarly you can talk about variance of x bar, which is nothing but 1 by n square plus 1 by n square plus and so on 1 by n square times sigma square. So this will be like n by n square of sigma square, which is sigma square by n. And what else we are left with? Yeah, that's it. So this is from here also we can prove that expected value of sample mean will be mu, variance of sample mean will be sigma square by n.
And expected value of variance?
Expected value of variance doesn't come under sum, right? We just talk about this sample mean expected value because this sample mean is the scaled sum of each of the random variable.
Okay.
So when we talk about s square is actually x1 minus x bar whole square plus x2 minus x bar whole square and so on xn minus x bar whole square divided by n minus 1. So
why n minus 1?
Why n minus 1? That is what I wanted to ask. Why n minus 1? Why not n? Okay. So just now we have discussed this, right? Expected value of S square, sample variance is somewhat very nearer to sigma square, right?
Yes, sir.
Correct. So we will try to validate with, let us take, I don't know, n minus 1 or n. Let us believe this is true. So this is true because from the data, we just saw the data. By taking the data, my expected value of this sample variance is actually very much nearer and nearer to population variance. So this thing, will you believe?
Answer?
Yes.
This particular thing, will you agree? Expected value of the sample variance is population variance.
As n increases.
As n increases, as number of samplings we do. So ultimately we reach to this.
Yes.
So using this, we can actually say that this will be n minus 1, not n. Also, if we are going to study biased estimators, unbiased. Once you study estimators, we study biased estimator and unbiased estimator. This particular S square is actually a random variable, and this is an estimator for this population variance. See, this S square is an estimator, one estimator. So one good estimator, we say. So this S square, if we divide it by n minus 1, this will be an unbiased estimator. If you divide it by n, that will be a biased estimator. So I will just show you very simply. Try to understand. If you understand, even though if you didn't understand, do not worry, because it is not necessary to go through the proof. But it is important that n minus 1 gives you better, what we say,
estimation,
better estimators, better estimation to population variance. So this we take it as true. Okay, from here I will start. See, expected value of S square will be equal to expected value of, so I don't know the divided by n minus 1 or anything. I just say it is k, some k I should multiply. So k times, I have in the numerator I equals to 1 to some n xi minus x bar whole square. Expected value of, sorry, xi minus x bar whole square. Already I have written expected value outside. Correct?
Yes, sir. So you can take the k outside.
Even k can come outside. This will be like
Then
expected value of, just expand this.
Yeah, summation over xi square.
I is equals to 1 to n xi square minus 2xi
2 summation
x
over
bar
xi
plus x bar square.
Right.
Okay. So this will be inside the summation. Everything will be inside. Now this will be expected value of I is equals to 1 to n xi square minus 2 times x bar is also independent of n. So 2 times x bar, sorry, independent of I. Summation I is equals to 1 to n xi. So this term I just written like this. Correct?
Yes, sir.
Plus
Yes,
summation I is equals to 1 to n x bar square.
No, sir,
Now this
there
x bar square
summation
is
will not come, sir, because x bar is independent, no, sir.
x bar square I need to add n times, right?
Square.
nx bar square, it will be like nx bar.
Okay.
Now this is like summation I is equals to 1 to n xi square minus 2 times x bar, and this will be like x1 plus x2 plus and so on xn, plus this will be n times x bar square.
So it will be minus x bar square.
Which will be
minus
minus
n x bar square.
Yeah. This particular thing is nothing but n x bar. Correct? n times x bar. Am I correct?
Yes, sir.
So sample mean is actually x1 sum divided by n. So this sum will be n times x bar, and this is like minus 2 times n x bar square, and this is plus n x bar
Plus n
square.
x bar square.
So this whole computation will be simplified to minus n x bar square. Okay. Now I will take expectation inside. Now k times expected value of xi square plus x1 square plus x2 square and so on plus xn square minus n times
N into expectation of x bar whole square.
expectation of x bar whole square. Now till here it is okay. How do we compute this and this? So now this you should understand. If x1, x2, xn are independent, if they are independent, then x1 square, x2 square and so on xn square are also independent. Okay, this you understand, these things. Try taking some time, it's very easy to understand.
Yes,
If
sir.
x1
Yes, sir.
yeah. Now let us try to compute first and second terms. See this particular thing. Okay, let us compute this first. So expected value of x bar square, this I can get it from what is variance of x
Variance.
bar? This is expected bar x bar square minus
expected value of x bar whole square.
X bar whole square. So variance of x bar we know. What is it?
Sigma square by n
Is equals to expected value of x bar square minus
minus mu square.
Mu square. So this will be plus mu square. So this value will be mu square plus sigma square by n. Agreed? This particular term. And n times expected value of x bar square will be n mu square plus sigma square. So this particular term is n mu square minus of n mu square plus sigma square. Okay. Now this requires some understanding. Now see, expectation of x1 square. So what is the expectation of x1 square?
So again we can do the variance. Right?
Yeah, variance of x1 plus
expectation of xi
Expectation of
x1 whole square.
Whole square.
Yes, sir.
So what is variance of x1 here?
Sigma square.
Sigma square. So x1 is actually the same distribution which x follows, population. So the population variance plus
Mu square.
Mu square. And we have like this we have
n terms.
N independent terms.
So we get n into this particular thing will be n into mu square plus sigma square. Okay. Now how it will convert? K of n mu square plus n sigma square minus n mu square minus sigma square. Now this and this will get cancelled and we get
k into n minus 1
k into n minus 1 into sigma square. So with which we should divide. So what should be the value of k such that
1 upon n minus 1.
Expectation of sample variance will be sigma square, population variance.
1 by n minus 1.
1 by n minus 1.
So this particular thing should be 1 by n minus 1, so that this and this will get cancelled and expectation of sample variance will be the population variance. So that is why we divide it by n minus 1. If you divide it by n, then that will be like n minus 1 by n into sigma square. Expected value of sample variance will be n minus 1 by n into sigma square, which is different from population variance. And what actually turns out to be is this is not a best estimator for population variance. So this is a biased estimator. So depending upon the value of n, the variance keeps on changing. Okay, so that is not a good estimator. So we will study about what all the good estimators are, and every estimator we will study.
Sir, could you scroll a little bit, sir? Just for 1 second, sir. Slowly. Once more, sir. Once more. Now again, up. At the beginning, where yes, scroll up, sir. Scroll up. Yes, this part, sir. This part, sir. Here you have this. Where you have plot this one, that 2x bar, x1 plus x2 plus, up to xn. Can you explain this line only, sir? Then everything is crystal clear, sir. Yes, only these two lines.
This is 2 times x bar. See, this is I just took this summation inside each and every term.
Yes.
This summation will be like I is equals to 1 to n xi. So this is like x1 plus x2 plus and so on plus xn. So this particular term. So this will be like 2 times x bar and times x1 plus x2 plus and so on xn.
And the third term, sir, like summation of I equal to 1 to n x bar square, right?
X bar square is like.
But yes, but my x square bar is same, right? So what we are saying that every time I will add up to n times, right?
Correct.
Okay, so this line is done, and once I come down, sir, then from why we are dividing by n into x bar? Why are
no, we are not dividing. This particular thing is actually equal to n times x bar. See, this x1 x bar is actually x1 plus x2 plus and so on xn divided by n, right?
Yes.
Now take n to the left hand side. What is the x1 plus x2 plus and so on
x bar?
N times x bar.
So
that is what we replaced with this.
So it will become 2nx bar square, right?
2nx bar square.
Correct, and that's why 1 plus nx square bar, then so minus nx bar square, right?
This is 2nx bar square and plus nx bar square will be like minus nx bar.
Now got it, sir. Now got it. Yeah. Thanks a lot, sir. Sir, one honest feedback, sir.
Okay.
This kind of experience I have got for the very first time, sir. For the very first time.
Okay. But
and what you were saying, sir, that as n increases, right? So what happens as n increases, so the ratio n by n minus 1 becomes same, almost same, negligible. So that is the reason why it is being said that as n increases, then we can divide by n also, right? Am I right, sir?
Yeah. See, when we talk about population, we actually divide it by n.
Yes, correct. Thank you, sir.
Yeah.
Sir, which book to refer for this kind of derivation, sir?
These kind of derivations I have done in my masters.
Okay. No, sir, it is there in the reference book. The reference book that is given, it is there.
Which reference book?
I think it was given like some professors of ISI have written the book, the main reference book.
Thank you, sir. Thanks for explaining, sir.
Okay.
Reference book is Shivadreya. Shivadreya.
Yeah, that one.
Okay. One more doubt, sir. Actually, in that expression, sir, top set that E of x square, that is x1, x2, x3. Somewhat this one, sir. This one, below one. This below that. Yeah, it is mu square plus sigma square. That I didn't understand, sir.
Which one? This one.
E of x1 square, x2 square. Yeah.
See, this particular thing is actually use the expectation of linearity. This will be like x1 square, expectation of x1 square plus expectation of x2 square plus and so on, expectation of xn square. Correct? This particular thing will be this.
Yeah, sir. Yeah.
Now what I did is I have computed for one xi. So each and everything is identically distributed. So even for expectation of x1 square, this is nothing but these all are same. And so on. This is simply I can write it like expectation of xi.
Right. Understood. Thank you.
So variance of xi. These all are sigma square plus mu.
So you're not audible.
Are you there? He has lost the connection. Last time I was saying that every time his connection gets lost.
Hello?
After 2 years. Yes, sir. Are you there?
Yeah.
Okay.
See, we lost our power here, so I just connected with mobile. Okay. So I have connected with. Am I audible?
Yes,
Yes,
sir.
sir.
You're very much audible.
Your
Yeah,
system
okay.
is kicking you out at 10 o'clock, sir.
I don't know why.
last
See,
time
this is
also
happening even for me. Today, luckily, it didn't happen yet.
That's what I was
I
saying,
think
sir.
it will happen with.
Last time only you told the story that every time this happens with you.
Yeah, every time this happens for
And this
every
happens,
2 hours, I guess.
This happens only with you, sir.
I don't know. I need to check. Okay, so this is the derivation, and on top of this everything, you don't need to go through this derivation if you believe this. If you simply believe that it is divided by n minus 1, nothing required. These all are these proofs actually gives you better understanding of why that is divided by n.
But sir, the underlying assumption is that they should be independent, right? The underlying
IIDs. These exponents are actually the IIDs.
IID. If they are not, then whether this definition will violate, sir? This n minus 1 division by n minus 1 will violate?
No. See, these actually, whatever the samples we take, these samples are actually taken from one distribution only, right?
Okay.
And one
Sir,
sample
when we are doing the samples, like when taking the samples in a random way and like in an independent way, so then the variables that we get, it will be IID.
So
like
by default,
it
will
will
be
always be the
IID.
case.
That's what Vinayak was saying. By default, it will be IID every time, right?
Yeah. It was said in the lectures.
These are IIDs. See, whatever the samples we take from the population, those will be IIDs.
Sir, I have a small doubt in that empirical distribution. Can you just say how it is becoming, or how it is a PMF? Like it is a PMF, but I am not able to what is the values and what are the probabilities?
Which question you are talking?
The empirical distribution. The x1, x2, xn is IID. Then the probability is like 1 by n, and n into like the hash xi equals to t.
See, number
like
of
the
times
number of
xi
times xi takes value.
Yeah, correct. See, this is like number of times. Hash represents number of
times.
times.
Number of times. Yeah.
Number of times these particular xi takes t
divided by n
is we can actually, this is the number of times we say t occurs in the sample, you can say, maybe. Okay, probability that x takes value t, or probability of t is actually number of times this t occurred divided by total number of samples. So this is actually, you see, you just simply take the Bernoulli distribution. To see why I am taking always Bernoulli is like it will give you good understanding, easier understanding. Then we can go for higher distributions. So let us say it is following, x follows Bernoulli 0.5, and these x1, x2, xn are samples, IID samples of this x. Now I just wanted to compute the probability that out of 10 tosses, I just wanted to compute how many. Okay, I just wanted to compute the probability of head. So I just take only 10 samples out of it. So if I take 10 samples, I may get head in the first toss. One sampling instance, if I take 1 0 0 1 1 0 0 0 0 1. Okay, so this is one set of 10 samples. Hello.
Yes, I'm there. Yeah.
Right. So how do I calculate probability based on this 10 samples? Is out
so
of
these
10
are
times.
These are my separate xis.
These are your separate x's. This is x1, this is x2. First toss, second toss, third toss.
So what I'm checking is that x1, say I'm taking equals to 1.
Yeah.
Then I am doing x1 is equals to 1. x4 is equals to 1, like that.
Yeah, x1 is equals to number of times 1 occurred. See, number of times heads occurred. I'm just curious that chance of head occurring, probability that head occurs. Okay. I just wanted to compute the probability of head, probability that x, or probability that head.
So when I'm saying that number of times xi is equals to t, that means t is fixed for me. T is equals to 1 over here.
Yeah, t is
so
equals
what
to
I
1
am
over here.
what I'm checking is what are the total number of random variables that are taking those values of 1.
So this will be
So
like
here
4.
it will be 4 by.
So probability that head appears is 0.4. This is what I will result, right? My result is like, I have tossed coin 10 times, only 4 times I got head and 6 times I got tails. So what I can say is the chance of occurring of head is actually 0.4 only. Out of 10 tosses, you will only get 4 times heads. So for one sampling. So how did I say this? Number of times heads appear divided by total number of times I toss the coin. Okay.
Yes, actually, there was a question in the reference book. There was a question. Actually, I got confused over there, so that's why I asked
Okay.
over here
So
empirical
this
question.
is how we actually derive probabilities. See, actually, this kind of form, whatever we say, coin toss is actually how we. Do you know how we got probability of head is 0.5? Probability, if I toss a coin, probability of head occurs is 0.5. So these all came by randomly. We start sampling. So we say prior, posterior. These all things will come in week 9, I guess. So prior distribution, posterior distribution. What we actually take it is, we actually believe that if you don't know the distribution, we actually believe that it is uniform. We take it as uniform throughout, and we actually take one random sample and we improvise the distribution by taking the prior distribution as uniform, and later by taking a sampling, then we come up to a posterior distribution which we actually improvise our distribution. So once we actually take the sample, so with that sample, see, if I take only 2 samples here, so the probability of head occur is 0.5, right? So out of 2 tosses, I got 1 head, 1 tail.
Yeah.
If I take 3, it is becoming 0.33. If I
Right.
take 4, it is actually becoming 0.5 again. So this is, for first toss, I have probability of success is 1. But that is not true. Even I know, everyone knows.
Yes.
Okay. But what I believe is my probability of occurrence of head is 1. I take it like that and I will do the experiment. So depending upon the result, I improvise my probabilities. So this is called posterior probabilities. So after one sampling, we actually improvise our posterior, improvise our PMFs. So while improvising our PMFs, if it is discrete random variable, we improvise our PMFs. Ultimately, after so many number of samples, we actually come up to the actual distribution. So these are called Monte Carlo simulation. We actually simulate infinite number of samples, and we actually come up that out of that many infinite number of samples we done, half of them are heads and half of them are tails. So from there we actually get our value, probability that head appears is 0.5. These are some interesting things to look into.
Sir, so there is a small, in the empirical distribution, there is a small doubt in the question. I'm just saying it. So the question was given like, let P be the empirical distribution defined by the sample observations x1, x2, ... xn. Then it is said that let y be a random variable with distribution P. Then it was given to show that expected value of y is equals to x bar and variance of y is equals to n minus 1 by n s square.
Expected value of y is x bar.
X bar. and variance of y is equals to n minus 1 by n capital S square, like the sample.
Okay, so this is x1 to xn, and we have,
and P is the empirical distribution defined by the sample observations x1 to xn. It is the empirical distribution, that you just wrote, that thing, I guess.
okay,
It was
where are
written
these
in other
x1,
words.
x2, xn are coming?
It was written in other words. P is the discrete distribution with probability mass function given by the definition, that the empirical distribution.
Okay,
those are the
that is
sample
okay.
observations.
Samples taken from population. What is the population here?
It was not given, like just it was written that let P be the empirical distribution defined by sample observations x1 to xn, and it was written that in other words P is the discrete distribution with probability mass function that was given by the definition, like the normal definition of empirical distribution, PMF, that was given. Then it was given let y be a random variable with distribution P, then it was asked to show this too.
Okay.
Yeah, this is one of the questions from the reference book. Like I completely, it was going above my head, so I.
Okay, we will see this at the end of the lecture. Okay, if you can hold for some 15 to 20 minutes, let everyone leave the session at 10:30. We will discuss.
Okay, sir, no problem.
Okay. Yeah. So next thing I wanted to discuss today is weak law of large numbers. So the name itself tells us right. So what does this weak law of large numbers tells us? So if I have my samples, number of samples to be more and more, if I have more number of samples with me, then my sample mean and the population mean difference. So there is a difference between sample mean and population mean, right? This particular difference means mod of either mu greater or lesser, we don't worry. If this difference is large, so something larger than some delta, so the probability that the difference between these two will be greater than some delta will actually be less than or equal to sigma square by n delta square. So what are these sigma square and delta mu r is? So if I have some random variables x1 to xn, iidx, where this x has parameters, expected value of x is mu and variance of x is sigma square, and yeah, from here x bar is nothing but x1 plus and so on xn by n. So the expected value of x bar we know mu, expected value of variance of x bar is actually sigma square by n. So these all things we know. So these are all given to us. So if these are given and we know this n is sufficiently large. So what I mean sufficiently large is actually n is greater than 25, we consider as sufficiently large. Okay. So if n is greater than 25, or sometimes many people will say 30. So we consider if n is sufficiently large, then the sample mean. So we already just now we have seen in the sheet also. If I have some 35 samples with me, so that is a sufficiently large. So the sample mean and the population mean difference is actually coming closer and closer. So if I say if that is greater than some delta, the probability of that will be lesser than or equal to sigma square by n into delta square. So this in other words we say probability that x bar minus mu lies within some range. So this is mu.
So
Let's say
does
this
it
is
come
mu.
from the Chebyshev's inequality?
It will come
Like
from the
it is
Chebyshev's inequality.
like very similar to, looks very familiar.
You know Chebyshev's inequality, is it? Did we discuss Chebyshev's?
Yes, sir. It was there in the week 4 or something.
Then it is very easy to
Markov's
understand.
inequality and Chebyshev's inequality.
Yeah, correct. I got it. So what Chebyshev's tells us? So if I have
sir, in Chebyshev it was 1 by k square, sir. So please complete it, sir. So how we have it? In case of Chebyshev, it was 1 by k square, right? Hello, sir, am I audible?
I think Sarah has lost the connection.
You are audible, but sorry is missing.
Thank you.
Yeah. Hello.
Yes,
Yes,
sir. You are audible, sir.
Yeah, this is what happens. I'm
Once
not.
again,
See, let me tell you one thing. I am not exiting. Okay, don't.
I know, sir. We know, sir. We'll have to call them, sir. Now.
So yeah. Just a second. No? Okay, let me get coast access Momo. So,
sir, what is your ID on Discord, sir? It is 1729 or what?
Yeah, Srikanth 172. So, how many of you know?
Pardon?
What is the? How many of you know what is the importance of the number 1729?
That's some Ramanujan number or what?
Correct.
Ramanujan number, some
12 cube plus 1.
12 cube plus 1 cube. And what are the properties? There are many properties of Ramanujan number. So 12 cube plus 1 cube is one thing. Okay, I agreed.
Yeah, the number he saw, like his friend saw in a taxi, behind the taxi number, right?
Right. That is correct. So when he is in the hospital, G.H. Hardy is his professor. So he came to see Ramanujan when he is on the hospital. Then Ramanujan just sees the taxi driver number. So actually Hardy comes like he made late, and even though he doesn't have a fancy number, like he was like such a bad number he also has on that. And Ramanujan got interest in that, and he just asked what is the number, and he was like something like 1729 or something. Then on the bed, on the deathbed, actually he's about to die. Even at that situation, he was like, Ramanujan was like, 1729 is the smallest natural number that can be written as sum of two cubes in two different ways. So one is like 1 cube plus 12 cube, and other one is like 10 cube plus 9 cube. Okay, 10 cube plus 9 cube is also 1000 plus 729.
That is 1000 plus 729. Yes.
and 1 cube plus 12 cube is also 1728 plus 1 1729, and he reads some 3 to 4 properties of 1729 before he dies. And G.H. Hardy was awestruck after listening to those things. So that is why Hardy has given name that number as the Ramanujan's number, and that is how they are making late. Just give me 1 second.
Sir, no problem, sir. Sir?
Huh?
Yeah, once you get the connection, we'll go back to our main discussion.
Huh?
So, but one of the, he has done so many biggest invention. One of the things like how he proved that adding positive numbers, he got the result -1/12.
One second. Even I will prove. Hello, bro. What a co-host panning, bro. Yeah. Yeah, even.
No, now so many people are proving it, sir. But thinking intuitively, it seems counterintuitive. Like we're adding positive numbers 1 plus 2 plus 3 plus 4 like this infinite series, and we are getting -1/12.
-1/12. So have you seen the proof of it? Even I was.
I have not understood it completely, sir.
Is it?
I have seen couple of proofs on YouTube.
Okay, let me complete what all things I am left with. Let me complete this.
Yes. No, we can discuss some other day, sir. Not today. We have so many topics are left, sir. Weak law, class number, and then concentration phenomena.
Yeah, concentration phenomena. What I don't want to deal with concentration phenomena. Concentration phenomena is a small topic, and don't spend much time on that topic.
Sir, 3 inequalities have been covered in that topic.
3 inequalities has been covered in that. It is your interest. If you wanted to study, you can study. But today I want to cover that thing and moment generating functions.
Yes, okay.
So these MGFs are connected.
Yes, MGF is also very much important. Yes, that's why I was coming to that. So many topics are still left.
So MGF will connect to 7.6 lectures. So other than MGF, this concentration phenomena.
But now 7.6 has moved to 8.1.
Yeah, 8.1. Correct. So yeah. See, this concentration phenomena actually gives us some bounds. Okay. So if there are some exponent, it gives us some exponential bounds. So for that we actually use this concentration phenomena concept. Apart from that, this is important thing to study, but later what we decided is lots and lots of content we are discussing in stats 2, and students are getting confused what to study, what not to study, which one is important, which one is not important at this stage.
You've got the connections.
Yeah. So for that things, what we did is we have moved some contents which are not necessary as of now, but if students has an interest to study, then they can go into that additional content and they can study.
Sir, before you lost the connection, sir, we were discussing about that inequality. So I think we said that this was discussed in Chebyshev's distribution. Sorry, Chebyshev's inequality. So I was reaching a point that in Chebyshev we had discussed less than equal to 1 by k square, right?
Yeah.
But here it is sigma square by n delta square. So
I will prove. I will. So Chebyshev's inequality, if I have some random variable x and with mean mu and variance sigma square, then probability that this random variable mod x minus mu is greater than some k will be less than or equals to variance of x. Okay, I will write it as like this, minus expected value of x divided by k square. Right? This is what Chebyshev's inequality is. Correct?
Yes, sir.
Now, just see here. We want our random variable is x bar here. Okay. Now our random variable is x bar. And what is the expected value of x bar? Mu right? Expected value of x bar is nothing but the population mean. So which is mu. And what is the variance of x bar?
Sigma square by n.
Correct. So sigma square by n. Now see, just replace x bar as now replace x with x bar. What we get? Probability that mod x bar minus expected value of x bar greater than some k is actually less than variance of some x bar divided by k square. Now just substitute these values. We get probability that mod x bar minus mu greater than k is less than or equal to sigma square by n divided by k square. And k or delta, it doesn't matter. You can just write it like this. Mod x minus mu greater than delta is less than or equal to sigma square by n delta square.
Got it, sir.
So this is weak law of large numbers. Okay. So this actually, what this actually tells is, as n keeps on increasing, this particular probability will very much go closer to 0. So that means the difference between x bar and mu will come closer and closer. So this x bar comes closer and closer to mu as n increases. Okay. So this particular thing can also be written like this: probability that mod x bar minus mu is less than or equals to delta is nothing but greater than or equals to 1 minus sigma square by n delta square.
Within that band. Within that
Yeah,
band.
within that band. So yeah. So if this is x bar minus mu value, so this is minus delta. So that the value lies outside, probability that the value lies outside of this interval is less than or equals to sigma square by n delta square. Then the probability that x bar minus mu lies within this minus delta 2 plus delta will be 1 minus sigma square by n delta square, because which will be greater than. So if this is less than, this will be greater than, because the sum should be 1.
So this is greater than 1 minus delta square by n minus delta square.
Correct.
Right?
Yeah. This probability is greater than 1 minus delta square by n.
1 minus sigma square.
Sigma square by n delta square. Okay, this is weak law of large numbers. And
so this is at least. This must be at least, right? This must be at least, since it is greater than equal to. So
it is at least. Correct. So there are few examples in activity questions also. Try solving it. Any doubt in that activity questions with respect to this weak law of large numbers? You can ask it here now. No? Okay, let's move to movement generating function then. So yeah. So movement generating function of any random variable x we are going to generate. Okay. So movement generating function is actually expected value of e to the power lambda x. So this is the actual MGF means. Moment generating function simply means the expected value of e to the power lambda x. Nothing what I say, okay, what this moment generating function gives me is, this actually gives me the moments. So we know first moment, right? What is the first moment of any random variable?
So this is not important.
Huh?
First moment, second moment.
Yeah. First moment is actually mean. Mean is the first moment we call. How many of you know this first moment is mean?
Yes, sir. First moment.
No.
Okay. What is the second moment then?
Variance.
Right. Likewise, it will give us the moments. It will give us the third moment, fourth moment, fifth moment. So we can generate.
So these are the central moments that you see.
See, these are the moments. So, yeah,
Because
central
I have
moment.
seen in some of the books they distinguish between like the two more central moments and just moments.
See, central moments are like we centralize. We make expected value of x to 0. We bring the mean of that random variable x to 0. We centralize it, and then we compute the moments, first moment, second moment, and third moment. So those are central moments. Centralized. So we make it centralized, and then we compute MGFs. So that is why they are called central moments. Okay. So even here, see, that is what we should do. What we have to do is, first and foremost thing is this particular moment generating function will be e to the expected value of e to the power lambda x only for expected value of x is equals to 0. Okay. So in the lecture also, I guess professor has discussed this. Centralizing, how do we centralize the distributions?
He said so that all data points should be, we have to remove x bar, like x minus x bar.
Yeah, correct. We have to remove the x bar and it will centralize. So once it is centralized, then it will be easier to compute moment generating function. So one
That means
example.
mean we are equating to 0, centralizing.
Yeah, mean we are equating to 0. So I guess in order to better understanding, let us take x, some random variable x, which is, again I just want to take Bernoulli, but this time I just wanted to take not 0.5, something like 0.4. So now we have x is the following Bernoulli 0.4, so x takes either 0 or 1, 0 with probability 0.6 and 1 with probability 0.4. So the expected value of x will be 0.4, right? So what I wanted to do is, I will actually subtract. So this is called centralization, centralized x. So centralized x follows 0 minus 0.4 and 1 minus 0.4. So this will be equal to, this is equals to minus 0.4, this is 0.6, minus 0.4 with probability 0.6, 0.6 with probability 0.4. So if you compute the expected value of this centralized x, it will give us minus 0.4 times 0.6 plus 0.6 times 0.4, which will be 0.
So can you just say it? I just lost the connection. I was not able to hear you.
Okay, so what we did is I just took an example like x is following Bernoulli 0.4. So x follows, x takes 0 or 1 with probability 0.6 and 0.4. So the expected value of x will be 0.4. But I just wanted to make the centralized Bernoulli. I just wanted to bring the mean of this Bernoulli to 0. So what I will do is I will subtract this 0.4 from every possible value. So I should subtract 0.4 from 0, 0.4 from 1. So once I do that, I will get the centralized excess. It will take values minus 0.4 and 0.6 with probabilities 0.6 and 0.4.
One small clarification.
Okay, so expected value will be 0.
Expected value will be 0.
Sir, one small clarification. Like whenever I am changing my original data set, right? Doesn't it mean that I am changing I am playing with the distribution of original data set also? Say for example, if I collected the heights of 1,000 students, right? And just to make its mean 0, now I am subtracting the mean of all the data points from each individual data set, right?
Correct.
So whether it impacts my underlying distribution also?
No, it was like said in the standardization.
Okay, so it
It's
doesn't.
actually we are translation and
so it doesn't disturb underlying distribution.
Underlying it doesn't disturb. See, if your distribution is like this,
yes.
If you centralize, it will be somewhat like this.
So this is true for all the distributions.
Yeah, all the distributions. Okay. So if you centralize it, if you subtract the mean, whatever the mean is there, if you subtract it, it will come like this, and this mean will be 0.
Sir,
it will only the same distribution it follows, but it is actually shifting or translation happens.
And this is true for all the distributions.
One by one. Yeah, this is true for all distributions.
Okay, thank you, sir. Yeah, Vinay, you can question. Sorry.
Yeah, so I have a small general question, like say x and y are two continuous random variables, and they have the same distribution x and y. Then if I take suppose a function, say a real valued function from R to R, and I say fx and f of y, then will they also have the same distribution? Or
so
they can
it depends on the function you define. Both the functions you define are same, is it?
Yes, for both f, like small f, say.
Small f's are same, and both your xy distributions are same.
Same, they are same distribution they are following.
Then it will be same.
Then it will be same, right?
Yeah. So x, whatever you are saying is x. If x follows y, f of this x follows f of this y. That is what you are asking, right?
No, I am saying that x comma y follows some distribution. Like
x comma
it's a
y.
same. It's a
okay. Following Bernoulli means x is same. X is identically
say
distributed.
Say Bernoulli. Yeah.
So x is identically distributed to by y, right? Identically.
Yes.
Yeah.
Yes.
Correct. So this follows.
Then fx is also identically distributed to f of y, right?
F of y, correct. Okay. Yeah. Now where we are, once we centralized it, we can actually find the moment generating function, which is expected value of e to the power lambda x. So what is this? So x takes 0, x takes minus 0.4 once, and x takes 0.6 once. So the expected value of this e to the power lambda x will be probability that x is taking minus 0.4 times e to the power lambda into minus 0.4 plus probability that x is taking 0.6 times lambda into 0.6. Correct? So how do we find the expectation of this particular e to the power lambda x? Probability. So this is nothing but expectation of some. How do we find the expectation of x? So x takes
the probability values. We multiply by the probability values.
Probabilities and
add it.
That value. Yeah. So that is what we did. So probability that x takes minus 0.6 is 0.4 is 0.6 times e to the power minus 0.4 times lambda plus 0.4 times e to the power 0.6 lambda. So this is the moment generating function for centralized Bernoulli 0.4. So from this, what do we get actually?
What is the physical meaning of moment generating function? What do we call as a moment? What we are generating? What is a moment here?
Yeah, this actually, if you expand this e to the power lambda, and if you look at the coefficients of e to the power x, so what is the expansion of e to the power x?
1 plus x square by 2.
Factorial 1, yes. X square.
Plus x cube by 3 factorial plus.
Right. So now, what will be the expansion of e to the power some lambda x?
1 plus lambda x by 1 factorial. Lambda square x square by 2 factorial.
2 factorial. What do we get from this is, see, this is actually the expectation of e to the power lambda x, and this is the expectation of this, and this will be 1 plus lambda into
Lambda by
expected value of x by 1
yeah.
factorial plus lambda square into expected value of x square divided by 2 factorial plus and so on. See, if I look at now, I am actually, if I know the expansion of this, if I know the moment generating function with me, this as a moment generating function. If I expand this and look at the coefficients of lambda square, sorry, coefficient of lambda by 1 factorial, lambda square by 2 factorial, I am actually getting the expected value of x, expected value of x square, expected value of x cube. So like this. So these are the moments.
Okay, so we are not getting the variance directly. We are getting expected value of x square. Then we can.
Yeah, from there we actually get the.
These are the moments against 0, x is equal to 0, or the moments against the mean.
Moments?
I mean, moments got to have some reference point. It is not. I mean, I'm just imagining from the physics point of view.
Okay.
So moments means with respect to certain fixed point, then something is happening. So force is acting on something, so it's moving around.
Oh.
How do we really correlate
No,
that?
I think these values are called the first moment, second moment.
See, these are called moments. That's it. These are not physical.
I'm trying to understand why did it get that name?
I think because we are shifting that origin.
Shifting that origin to mean, to 0. Can you please scroll up, and you are explaining somewhere when the normal distribution curve type of thing is really shifting to the, yeah, right over here. Can you please relate these two things? Are we shifting the left to the right?
This right, yeah, left to the right. So this particular distribution will have some positive mean, some value mean.
Yeah,
but what we are doing is we are centralizing it. We are making it to
mean is 0.
0.
You are translating it then.
Yeah, translation. Some scaling and translation. We are making mean to 0.
For what we do that?
For to get the moment generating function, maybe.
All right, let's move. Thank you, sir.
Okay. So can you please show as to how to get EX and then EX square from there, comparing those two equations?
How do we get?
Yeah, get those values.
Okay.
So he's trying to say that to expand this and then compare and show that. Yeah.
Correct. Okay, what is the expansion of e to the power minus x? It will be like 1 minus x by 1 factorial plus x square. Correct? So this will be like 1 minus 0.4 lambda divided by 1 factorial plus 0.4 lambda whole square divided by 2 factorial and so on, plus 0.4 into
X
1 plus
0.4 into 0, 1 plus.
And so on. So now if you add these two, you will get 1, and this will be like minus 0.6 into 0.4 into lambda plus 0.6 into 0.4 lambda divided by 1 factorial plus 0.6 into 0.4 lambda whole square plus 0.4 into 0.6 lambda whole square divided by 2 factorial and so on. So you see here, this particular lambda term gets cancelled. 1, you understand this? 0.6 times 0.4 lambda by 1 factorial. This is minus 0.4 times 0.6 times lambda by 1 factorial. And this is plus 0.4 times 0.6 times lambda by 1 factorial. This and this will get cancelled. And we will have 1 plus, and this will be like 0.6 into 0.4 whole square plus 0.4 into 0.6 whole square and times lambda square divided by 2 factorial. So from here itself, if you don't, we are not having the lambda term. What does it actually give you if you don't have the lambda term?
Mean is 0.
Mean
Expected
is
value
0.
of x equals to 0.
Expected value of x is becoming 0. So why the expected value of x is 0? Because we actually
have
centralized it.
Yeah.
Okay. Understood?
Yeah.
Yes, sir.
Yeah.
Sir?
Yeah. This actually, this particular moment generating function actually gives us moments. These are called moments. Mean is called one moment. So for mean is actually a parameter. Some say parameter, population parameter. Some say it is actually one moment. And the second moment is actually called as
variance. Spread.
Spread. Second moment is called spread. So depending upon these moments, we actually define our data. So that is why these particular things are called moments.
Sir, but the second moment, if I just say the word, then it is not variance, right?
But it is related to variance only.
So the
it is related, but it is not variance because it is expected value of x square. So that is not variance. Like if I'm saying the second moment of x, then it is expected value of x square, which is not variance.
Sir, can we say that the formula of variance is expected value of x square minus ex whole square, right? So my mean is 0, so ex whole square is 0. So that is the reason why this expected value of x square is nothing but variance only. Can I say by that logic?
Here it becomes
yes. When I'm centralizing it,
yeah.
when I'm centralizing it,
when you centralize it, yeah.
When I'm centralizing it, then my expected value is 0, right? So ex is 0. And now formula variance.
But when I'm centralizing it, actually I'm not taking x. I'm taking x minus mu or something.
But your expected value of x will be 0, no? Like, while I'm doing
yes, that's why. So when you're doing expected value of x square, it is actually expected value of x minus x bar whole square. That is variance.
Correct. But no, see, at the start only, I think you also said that it is done for simplification, right? And it does not change my underlying distribution, right?
Yes. That is okay. That is okay.
Yeah. So while I have shifted it, my mean has become 0 of new data set, right?
Yes.
So this variance is the variance of new data set. So whatever I am projecting, I think that this is my thinking. I may be wrong. So that is the reason why here we are calling it as variance.
No. Okay, I understand now. See, there is a difference between moment and central moment. So moments are actually, so these are expected value of x power n. This is the nth moment. Okay. So actually this moment generating function gives us the moments. So the first moment is mean, the second moment is expected value of x square, third moment is expected value of x cube. So these are called moments. So this moment generating function actually generates these moments. So that is why that is called as moment generating function. So it actually gives us the moments. And there is one more thing called central moment. So this central moment is actually expected value of x minus mu to the power n. Okay. So if n is 1, this is actually the centralized mean. Centralized, or if n is 1, what happens? This will be expected value of x minus mu. Correct? And this will become 0. So the central moment, first central moment will be expected value of x. Centralized, for the centralized distribution, we call it as central moments. Okay.
Yeah, for the second central moment, it will be variance.
The second central moment is x minus mu whole square. What is this?
Variance.
Variance. Okay. So the second central moment is called the variance. Okay. The first central moment is actually the mean, and it will be 0 because the centralized distribution has mean 0.
But this we call when we are studying central moment, right?
Yeah, central moments. Then we call this as first central moment, second central moment. Second central moment is the variance.
Okay, and in case of moments, any moment, so that in that case it will be ex square, right?
Ex square. That's it.
So that's what Vinayak is asking. That's not variance.
That's not variance. So expected value of x power n is the nth moment. So actually this moment generating function actually generates these moments. So just now we've seen, right, this particular expected value of e to the power lambda x generates expected value of x, expected value of x, these moments. So this particular thing is called moment generating function.
But from the moments, can we always derive the central moments? If we know the moments.
From the moments, yeah, we can actually find the centralized moments, right?
Okay.
Yeah. And yeah, there are some usages of these MGFs in this lecture. So, okay, difference between moment and central moment. Correct?
Yes, sir, clear.
Okay, right? Yeah.
Yeah.
Now there is if x1 and so on, xn is IID x. What is the sum? So how do we generate the moment generating function for the sum random variable? So this is same expected value of e to the power lambda s, and this is like expected value of e to the power lambda of x1 plus and so on xn, and e of e power lambda x1 times this is like e to the power x plus y, e to the power x1 plus x2 is nothing but e to the power x1 times e to the power x2, right? Likewise I can write it as.
So is the moment generating function for any kind of like any distribution, is it always unique?
Yeah, unique, right?
I don't know, like I'm asking.
Unique. Any distribution will have unique mean, unique variance.
Oh, no, I'm talking about the distribution function. It is always like the moment generating function is always unique.
For one distribution, you are talking about
for a particular distribution.
For a particular distribution, we can actually find the moment generating function, and that particular moment generating function is unique. Okay. Yeah, and also from moment generating function, we can actually find the distribution. We can actually come back. So if it is not unique,
that's what I'm asking.
Yeah, if it is not unique, then you cannot actually find the distribution, right?
Yeah. Okay.
So this will be like lambda xn. So if you simplify this, see, I said IID x. So this is like e power lambda x whole to the power n, something like this, and this is e to the power lambda x whole to the power n. Okay, so what we got is actually, if we are looking at the sum of independent random variables, our moment generating function is actually the product of individuals, right? It is actually the product. So if I write it from here itself, I can write it as e to the power lambda x1 times expected value of e to the power lambda x2, like this. This will be the product of random variables if I look at the sum. Okay, and there are some bounds on this things also. If I talk about bounds, I should talk about concentration phenomena and everything. And what we made as new system, new in this new syllabus is restructured syllabus is we actually ignoring concentration phenomena. It's up to students' interest to learn this concentration phenomena, to understand this concentration phenomena. So if you have doubt, if you have gone through that concentration phenomena, if you are facing any trouble in that concentration phenomena, then we can discuss on that. Apart from that, this is about the moment generating function. So
sir, and
I am done with this, and
Sir, I
yeah,
have
small doubts you can stay back. Yeah, just please.
Sir, I have not done the
for
concentration that you're talking about. Can you just like what is it? Can you just like give a small like?
See, it's actually concentration phenomena is actually used to bound using exponential bounds. You can give exponential bounds to your probabilities. Okay.
Okay.
So this particular whatever till now we discussed MGFs and everything. So the probabilities also can be bound using this Chernov's. See, whatever the Chernoff Markovs we learned, those also actually gives us bounds, but it actually gives the bounds in 1 by n's, right? So so depending upon the n, it will actually doesn't give the proper bound, better bound. So for better bounds, we actually bound it using exponential. So e to the power some lambda t kind of things. So we will actually bound this x bar minus mu or x minus mu greater than delta. We actually bound it to exponential. Exponentials actually is better than this 1 by n's. So even the graph goes very steeper or very steeper, right? You know exponential curves, how it will take turns. So this particular exponentials will give you better bounds than the Chernoff and Markovs.
Not today, but in the next class, if you can.
Sorry, Chevyshevs and Markovs. Chernoff is actually the.
That's a third inequality what professor has described. Markov, Chebyshev, and Chernoff. So not today, not today. In your next class, sir, it will be better if you can spend 10 minutes, at least 10 minutes. So even towards the end of the session, that will be fine.
Okay. End of the session, we can spend some time of.
Like for weekend, when you come next Friday, then after completing the content of week 8, sir, at the end of the session, we can discuss something around this.
See, that is what I am saying. What I request from you guys is you better go watch it first.
Yes.
Yeah, okay. Then we can discuss better discussion will happen. Okay.
Sir.
Yeah. Yeah. So I am done, and thanks for joining, and have a good day. So a small doubts you can.
Sir, I have done that this one.
Which one?
Last additional content, sir, bounds. Upper bound and lower bounds. Actually, that e power. What we have done that MGF. That e power lambda by t by 4, which they given.
E power.
For lambda t square by 4.
Lambda t square by 4. Yeah. Huh. Where it is given?
In expressions, when lecturer discuss about this.
Sir, I think he's reflecting some examples, sir, where professor has taken the reference of those coefficient as the probability, and he's correlating it with this is the probability, like 1 by 4 is the probability 0.25. So something like that he has taken, right, Pawan? You were talking about that example. Yeah. So that
e power lambda square by 4, right?
Yes. Is this the thing you are talking about?
Yeah, sir. Yeah.
So how this is bounded? So how this particular value is less than lambda square by 4 is your doubt, right?
Yeah, and why we are discussing about bounds here? Actually, I understood that x minus mu less than or greater than delta. I understood. Whereas this particular thing I didn't understood, sir. Where this bounds I didn't understood. Upper bound and lower bound.
Okay. There is a lower bound here.
No, I'm thinking that x minus mu plus delta or minus delta is there, no, sir? When it is discussing, when we discussed on the top.
Okay. So x minus mu greater than some delta.
Yeah.
This probability is less than or equal to sigma square by delta square.
Yeah, I'm just correlating with this that they are talking about these bounds, upper bound and lower bound for this, because in that graph which they have shown, x minus mu greater than plus or minus delta, because it is in mod absolute value. So I'm thinking that upper bound and lower bound.
Okay, this has upper bound. This doesn't have lower bound. The lower bound is actually 0.
Okay.
N lambda square. N delta square.
And I am still, I don't have, I am still having doubt that what is your doubt? So
How this lambda square by 4 came, I didn't understand, sir.
This particular lambda square by 4. How that is what you wanted to know, right? Till now it is okay.
Yeah.
But this particular thing he has written it as like it is less than or equal to e power lambda square by 4.
Yeah, yeah.
Correct. So this has to do with some calculus part. So you know e power x by 2 plus e to the power minus x by 2 by 2. You consider this function, and this function has a maximum value. Will have a maximum value.
Minimum value at 1, 0, and
yeah. Okay, I will show you in the Desmos only. You know, do you know Desmos?
yes, sir. In Desmos, I draw that. It's a parabola at meeting at 1. At y-axis, it is intersecting at 1.
So what is the maximum value it can take?
It can take infinity. Both sides, plus or minus infinity.
Okay, okay. Okay. 1 second then.
So is lambda any real number?
No, no, no. Lambda is a variable.
Yes, I'm asking like it can take any real numbers. That
it can take any real number.
no.
So this is how it is, right? Can you see this other function?
Yeah, sir. E power
to the
x
power
square
x square by 4. So you see this red curve is below this blue curve.
Right.
Right. Whatever the value this particular red curve takes, it will be lesser than the value this blue curve takes.
Yeah, sir.
Right.
Right.
So that is how he bounded this particular whole, which is having x by 2 and minus x by 2. He doesn't want it to write it beat like this. He just wanted to bound it to a simpler expression, which professor has taken as e to the power x square or lambda square by 2.
But even if it is x square by 5 also, it will be inside of this red curve, no?
X square by 5.
5 x square by 6 also it is inside only.
Yeah, x square by 5, x square by 6. Correct.
But especially they taken only x square by 4. Is there any?
See, I guess if you differentiate this function, what will you get? So you will get
power x by 2 e power x by 2 minus 2 e power x by 2 is getting 0.
Half and half, 1 by 4 you will get. E to the power x by 2 minus e to the power minus x by 2 by 4.
0. Oh, okay, okay. Non-zero. It's minus. Right.
Yeah, there is minus. See, there are some even I am not sure at this time. See, they actually bounded it with lambda square by 4. But this is a good question. I will just make some research on this. I'll just go back, read some books, and I will come back to you. Okay.
Right.
I will see why this is actually bounded to 4.
Sir, please take Friday session, sir. Okay.
See, Friday session I will try. If I have, I already said, if I have max on session, then I cannot able to come back and take Friday.
Sir, but stat is also very critical, sir.
Yeah.
At
See,
least one session we deserve, sir. No, your one session. We are not asking you to come for all 3 sessions, sir. At least for Friday, the concept revision session. See, today's session.
Even we did the same revision session. Even if we took this Sunday session.
No. On Sunday we'll discuss that. Sorry, on Tuesday we have solved with us. No, nobody asked conceptual question on that day, sir. What we had requested that one day should be for conceptual, the other day for activity, and the third day for solve with us.
Yeah. See, I will most of the time I will try. Okay, it's not like even I should get time on Friday, every Friday.
Please keep stat to also, sir, in your priorities, sir.
Okay, I will try. I will definitely try. I'm trying. See, if I didn't get Friday session, I am actually taking the Sunday session. Okay, I'm not taking that solve with us.
Then what happens around Friday, sir? Okay, that's fine.
What happens?
Nothing, sir. Okay, sir. Then in that case, we'll discuss concept on Sunday, sir. No problem.
See, the thing is, even maths one has limited resource
sir,
of
what
instructors.
happens just see today also, whatever micro steps are there, no, which is missing in the lecture, right? So when you are detailing it, it brings more clarity, sir.
Okay.
Sir, one last thing from my side, sir. This is purely I'm asking for out of curiosity, right? I don't want to discuss today, sir. Whenever you come next time, whenever we have some additional time, we can discuss. So in week 2 or week 3, whenever we spoke about functions, right? When we started talking about functions of random variable, right?
Yeah.
So we started with functions of discrete random variable. So we started our notion with IID, independent and identically distributed. So as a layman, I'm a typical layman. So whenever I'm hearing the word IID, immediately 4 cases come to my mind. That okay, there are possibilities that something can be independent and identically distributed. Something can be independent but not identically distributed, right? Something will be dependent and identically distributed, and something will be dependent and not identically distributed. Out of these 4 cases, we have studied mainly IID. So I was just doing the permutation and combination. We have covered 7 types of probability distribution for discrete random variable.
Okay.
So if I make all the permutation and combination, then it is coming around 105, which is a very crazy number. And I know that there won't be 105 types of discussion. So why I'm saying that will we studying all these things in higher courses, or it's a complete nonsense which I'm asking, and we have to concentrate only on IID? Like, just I want your take on this, sir.
Okay. See, why we study about IIDs is...
Hope I am able to understand. I am able to put my question, sir.
Yeah. See, the thing is, identically independent distributed random variables have few properties, and using those properties, we can actually derive few results. Okay, some results are actually being derived. Like just now I have said above, right? This particular thing.
Yes.
So sum of random variables is actually, if the sum of random variables
that is also
is actually is actually a random variable.
Yes.
If I am considering the sum, my moment generating function will become the product. Okay. Product of moment generating functions. So these all things are some few results to which excites us to learn more and interesting results. These are some.
In real life, my random variables may not follow always identically and independent. They may be dependent but identically distributed.
See, whatever the population you have, whatever the samples you choose, they will always be IIDs. One thing, if you choose one sample and the next sample, first sample, choosing the second sample is independent of choosing the first sample. Agree? So most of the scenarios which we are going to deal in real life are IIDs.
Okay, so this is one answer, that in real life most of the distributions will follow IID, right?
Yeah. So population and sample follow, whatever the samples I take from population, these samples will be IIDs.
Just to give one counter example, sir, like Professor Ramesh talks about IPL example, right? So say for example, scoring runs in an over will depend on number of wickets also. So they are dependent, no, sir, in that case.
Yeah, they are dependent.
In that case, they are dependent. So whether these properties will hold true in the
No, these properties will not hold. So you cannot derive anything new. So
even
you
in
should
that
actually.
case, so how to address that kind of problem?
You should address with the basic knowledge we have with random variables.
No, just try to extrapolate this example. So say for example, in real life, one company is launching some product, right? With an assumption that there won't be any competitor. But immediately some competition comes, and now that profitability will go down, right?
What is probability here?
No, I'm saying
profitability, I think.
profitability, not probability. Profitability or all their projections will go down, right? So real life situation is flooded with dependent cases. That's what I'm not. I don't want to...
Not always IIDs you are
Yes,
telling
yes,
that not
yes,
always.
yes, yes.
Yeah. See, the
That is my
profit, if your profit is a random variable here, okay, your distribution of that particular random variable changes, varies with respect to the new company, some new company. These things we call it as there is one technical term for this. So parameters, bias. What are these things which? What are the things which we don't have control in our hand and it affects
noise.
Yeah, noise, not noise. Other synonyms of noise.
Synonym of noise, uncontrollable variable.
Variables, some variables which we can control, some variables which we cannot control.
Cannot control, yes, sir.
Yeah, which we cannot control, and depending upon those variables, not variables. Variable is another thing. Depending upon those factors, correct. So depending upon those factors, our distribution varies. So considering those factors also, there is one technical term for this. See, bias is one technical term. So bias estimator, unbiased estimator. Depending upon bias and unbiased estimator, our distribution varies. Apart from biasness, we have one more thing. Bias. Error, bias.
Regulator or something?
Risk. There is one more term called risk.
Systematic risk, unsystematic risk.
No. See, this is the idea. This is the key. There is one term called let us say factors only. Let us consider factors only. Factors which we cannot control also affects our distribution.
Correct.
What we do is, we actually call in physics, we call it as noise, right?
Physics we call it.
Yeah. So there is one technical term for statistics. So even that particular thing, what we do is we take into the consideration of that, and we actually improvise our distribution. And then after improvising our distribution, if I take some samples, when I meant samples means this year's profit or this month's profit or today's profit is one sample, tomorrow's profit is another sample. If your company turnover, you are looking at day by day profit, or the stock price of your company, you are looking at the stock price of your company. So each day is your sample now. So after using all these techniques after considering all these techniques, your distribution, your complete population distribution varies, and the samples will remain same IIDs. Which we are going to deal will be the IIDs itself. So there will be whatever you said.
You're saying something, please.
Whatever you said, there will be some cases where maybe your random variables are not IIDs. Maybe you take each and every bowler's top speed. So not every bowler will bowl with same distribution.
Or may I request you, sir, that next time when you come, So if time permits, we can discuss more on this topic towards after.
Yeah.
Please keep a note of this also.
Sir, will you take one last question regarding today's lecture?
Yeah, sure.
Thank you, sir. Sir, my question is that suppose we took one sampling of say 10 samples, right? And we want to see if it fits a normal distribution. Now we are trying to calculate fx by hand, let's just say, like 1 by root over 2 pi sigma, that equation, right? And we calculate the values for fx, like fx1, fx2, fx like all 10. From there, how do we go about calculating the probability? Like we have calculated, we have found, we have got like x1, x2, x3, x4, x5. We have got, say, let's say we have taken certain weights or heights of people, right? And we have calculated those. And we have calculated the fx values for those 10 samples. Now, how do we calculate the probability? Of that
fx is actually the density function, right?
Yes, of course, sir. We have calculated the density function that way because we can, we know E, we know X, we know the other parameters, and we have done it, sir. From there, how do we go to, from fx, how do we actually calculate the probability by pen and paper or by hand?
So you want to calculate the probability of what?
Say within the 10 samples, I mean trying to fit a normal curve. Let's just say, let's find if the weight varies between this much and say between 50 or 60 or say 60 or 70. Like calculate the area between the one area of the curve, that is, sir. Anything thing will do.
Okay, so you are taking some random samples out of a population of normal, right?
No, I'm taking a random sample of weights. Say, let's say 50 kg, 60 kg, 55 kg, 32 kg, things like that. So there are 10, I've got like 10 values of my x1. Now I calculate fx for these 10.
Okay, you are seeing the weights of each and every person. And do you know the population mean weight?
I don't know anything at all, sir.
You don't know anything at all?
No. I just go to a room or a park or somewhere and I find out the weights of 10 people.
How do you calculate fx?
Okay. How do you computing fx here?
Yes. So I'm using my sample mean and my sample standard deviation here.
Sample mean and sample standard deviation, right. So this is actually you are estimating your parameters, right? You wanted to estimate mu, you wanted to estimate sigma square, correct?
Yeah, maybe, but I really wanted to go from fx to probability.
Yeah, you wanted to go from here to actual population distribution.
Yeah.
So you have randomly, out of this x normal mu sigma square, you have randomly choose some values, some weights, maybe 50, 32, 48, 72, like this.
Yes.
Correct. So now you have, you know this is normally distributed, or you don't even know that is also?
Well, I just want to try to fit in. If it's, I just want to find out.
Wanted to try to fit that in the normal distribution.
Correct? Yeah, right. I can calculate it in an Excel and see whether the curve fits or whether my data fits.
Correct. Just now we discussed the expected value of sample mean is the population mean.
Yes.
Okay. And expected value of sample standard deviation is the population variance. Expected value of sample variance is the population variance.
Okay.
Irrespective of what x follows. Right?
Right.
So now you have these many weights with you. These are the weights you have. So let's say you, not only 10, you have collected some 100 weights. Let's say. So you just compute the mean of this and you just compute the standard deviation of this or variance of this, and that will be the normal with mean mu and normal with mean sigma square. This is what you has taken some 100 samples, maybe 100 samples. Out of these 100 samples, we actually estimate your population mean to be equal to the sample mean. You are going to estimate it. If you have taken some other 100 samples, new 100 samples, what you do is you collectively you collect this 200 samples, make it 200 samples, and then you find the mean, you find the variance of those samples, and those will be equal to the mean of the population and variance of the population. Okay. Whatever we did till now is we know the population parameters, and using that population parameters, we have actually computed the parameters of samples. Correct?
Okay, now we are doing it the other way.
Now we are going it the other way. We know this is true for any distribution. This is true. So what we actually do is, if we have this data and if I wanted to fit it in this, what I simply do is, this is more or less, this particular mean will be very much nearer to the original population mean. So this mu denotes the mean here. So I will actually equate this sample mean to the population mean, and I will actually equate sample variance to the sample variance to the population variance.
Okay, this part is clear, but then how do I get to the probability part? Say finding the probability of my weight lying between say 50 kg and 55 kg.
So once you got this mu and sigma square, this is actually converted to normal mu sigma square, right?
Okay, then use the distribution table
Use
and
the
find out.
population distribution and
Okay.
integrate the density function in that.
Okay.
I think, sir, as you said at the beginning, that this will be discussed in week 9, right?
Yeah, yes. We will anyway discuss how to estimate these parameters. What are the good estimators for this?
Oh, I'm sorry. Is this like this is not from this week?
Yeah, this will come in the next week.
Oh, I'm so sorry.
Week number 9, I think it will come.
Yeah, week 9 we will discuss about the parameter estimations. So there we will actually estimate the population parameter, population mean and population variance and everything using the samples.
Got it, sir. Thank you.
Yeah.
Okay, sir. Thanks a lot, sir.
Yes, sir. Thanks a lot,
Thanks
sir.
a lot, sir. It was
Lengthy
really a
class.
great session, sir.
Okay.
Yeah.
Sure,
Please come on
thanks.
Friday, sir. Please.
Yeah.
Now only
We'll
4
try,
weeks.
Thank you, sir.
4 weeks are left, sir. We need only 4 sessions, sir. Please come.
Okay. We'll try. Thanks.
Thank you.
Thank you, sir. Thank you very much.
Thanks. Host, you can end the session.